Hello. All right, welcome everybody. Let's give everyone a moment to get back in the audience. All right, great. Welcome to Tesla AI Day 2022. We've got some really exciting things to show you. I think you'll be pretty impressed. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot. But now we've come a long way, and it's compared to that, I think it's very impressive.
You know, compared to that, it's going to be very impressive. We're going to talk about the advancements in AI for full self-driving, as well as how they apply to, more generally, to real-world AI problems like a humanoid robot, and even going beyond that. I think there's some potential that what we're doing here at Tesla could make a meaningful contribution to AGI. And I think actually Tesla's a good entity to do it from a governance standpoint, because we're a publicly traded company with one class of stock, and that means that the public controls Tesla, and I think that's actually a good thing. So if I go crazy, you can fire me. This is important. Maybe I've gone crazy. I don't know. Yeah, so we're going to talk a lot about our progress in AI, Autopilot, as well as the progress with Dojo. And then we're going to bring the team out and do a long Q&A. So you can ask tough questions, whatever you'd like, existential questions, technical questions, but we want to have as much time for Q&A as possible. So let's see, with that, you guys want to say anything?
Hey guys, I'm Milan. I work on Autopilot and the Tesla bot.
And I'm Lizzie, a mechanical engineer on the project as well.
Okay. So should we bring out the bot?
Before we do that, we have one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes, mechanical mechanisms, no cables, nothing.
Yeah.
I want to do it with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. It was on stage tonight. So the robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face. So we'll show you some videos now of the robot doing a bunch of other things, yeah, which are less risky. Yeah.
We should close the screen, guys.
Yeah.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot, and just walking around and dancing on stage. Just humble beginnings, but you can see the Autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up. Yeah.
We use the same process as we did for Autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more. And something that we'll try to nail down in a few months, over the next few months, I would say, to perfection.
This is really an actual station in the Fremont factory as well that it's working at.
Yep. So.
And that's not the only thing we have to show today, right?
Yeah, absolutely. So what you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out.
Do it.
So here you're seeing Optimus with with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. So that's incredibly important. I mean, you've all seen very impressive humanoid robot demonstrations, and that's great, but what are they missing? They're missing a brain. They don't have the intelligence to navigate the world by themselves, and they're also very expensive and made in low volume. Whereas Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000 would be my guess.
Okay.
The potential for Optimus is, I think, appreciated by very few people.
Hey!
As usual, Tesla demos are coming in hot. So,
Okay, that's good. That's good.
yeah. The team's the team has put in an incredible amount of work, working days, 7 days a week, burning the 3 a.m. oil to get to the demonstration today. Super proud of what they've done. They've really done a great job. I'd just like to give a hand to the whole Optimus team. So, now there's still a lot of work to be done to refine Optimus and improve it. Obviously, this is just Optimus version 1. And that's really why we're holding this event, which is to convince some of the most talented people in the world, like you guys, to join Tesla and help make it a reality and bring it to fruition at scale such that it can help millions of people. And the potential, like I said, is really boggles the mind, because you have to say, like, what is an economy? An economy is sort of productive entities times their productivity, capita times output, productivity per capita. At the point at which there is not a limitation on capita, it's not clear what an economy even means at that point. An economy becomes quasi-infinite. So what taken to fruition in the hopefully benign scenario, this means a future of abundance, a future where there is no poverty, where you can have whatever you want in terms of products and services. It really is a fundamental transformation of civilization as we know it. Obviously, we want to make sure that transformation is a positive one and safe. But that's also why I think Tesla as an entity doing this, being a single class of stock, publicly traded, owned by the public, is very important and should not be overlooked. I think this is essential, because then if the public doesn't like what Tesla's doing, the public can buy shares in Tesla and vote differently. This is a big deal. It's very important that I can't just do what I want. Sometimes people think that, but it's not true. It's very important that the corporate entity that makes this happen is something that the public can properly influence. So I think the Tesla structure is ideal for that. And like I said, self-driving cars will certainly have a tremendous impact on the world. I think they will improve the productivity of transport by at least a half order of magnitude, perhaps an order of magnitude, perhaps more. Optimus, I think, has maybe a 2 order of magnitude potential improvement in economic output. It's not clear what the limit actually even is. So, but we need to do this in the right way. We need to do it carefully and safely and ensure that the outcome is one that is beneficial to civilization and one that humanity wants. This is also it's extremely important, obviously. So, and I hope you will consider joining Tesla to achieve those goals. At Tesla, we really care about doing the right thing here, or aspire to do the right thing, and really not pave the road to hell with good intentions. And I think the road to hell is mostly paved with bad intentions, but every now and again there's a good intention in there. So we want to do the right thing. So consider joining us and helping make it happen. With that, let's move on to the next phase.
Right on. Thank you, Elon. All right, so you've seen a couple robots today. Let's do a quick timeline recap. So last year we unveiled the Tesla Bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real-life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. We're leveraging all of those learnings that we already have. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. We think that matters for a few reasons. But it's fun. We spend a lot of time thinking about how amazing the human body is. We have this incredible range of motion, typically really amazing strength. A fun exercise is if you put your fingertip on the chair in front of you, you'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, its main function is to do real useful work. And it maybe doesn't necessarily need all of those degrees of freedom right away. So we've stripped it down to a minimum sort of 28 fundamental degrees of freedom, and then, of course, our hands in addition to that. Humans are also pretty efficient at some things and not so efficient in other times. So for example, we can eat a small amount of food to sustain ourselves for several hours. That's great. But when we're just kind of sitting around, no offense, but we're kind of inefficient. We're just sort of burning energy. So on the robot platform, what we're going to do is we're going to minimize that idle power consumption, drop it as low as possible. And that way we can just flip a switch and immediately the robot turns into something that does useful work. So let's talk about this latest generation in some detail, shall we? So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue our electrical system. So now that we have our sort of human-based research, and we have our first development platform, we have both research and execution to draw from for this design. Again, we're using that vehicle design foundation, so we're taking it from concept through design and analysis, and then build and validation. Along the way, we're going to optimize for things like cost and efficiency because those are critical metrics to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. We're going to do things like reduce the sensing and the wiring at our extremities. You can imagine a lot of mass in your hands and feet is going to be quite difficult and power consumptive to move around. And we're going to centralize both our power distribution and our compute to the physical center of the platform. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one place. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce. We want to leverage both the Autopilot hardware and the software for the humanoid platform, but because it's different in requirements and in form factor, we're going to change a few things first. So we still are it's going to do everything that a human brain does, processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well. But before we do that, I'd like to introduce Malcolm, who's going to speak a little bit about our structural foundation for the robot.
Thank you, Lizzie. Tesla have the capabilities to analyze highly complex systems. They don't get much more complex than a crash. You can see here a simulated crash from Model 3 superimposed on top of the actual physical crash. It's actually incredible how accurate it is. Just to give you an idea of the complexity of this model, it includes every nut, bolt, and washer, every spot weld, and it has 35 million degrees of freedom. It's quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence a robot? Well, we can make a model. And since we had crash software, we're using the same software here, we can make it fall down. And the purpose of this is to make sure that if it falls down, ideally it doesn't, but it's superficial damage. We don't want it to, for example, break its gearbox and its arms. That's equivalent of a dislocated shoulder of a robot. Difficult and expensive to fix. So we wanted to dust itself off, get on with the job it's been given. We can also take the same model and we can drive the actuators using the inputs from a previously solved model, bringing it to life. So this is producing the motions for the tasks we want the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can play to the model. This is showing just simple walking. We can create the stresses in all the components. That helps us to optimize the components. These are not dancing robots. These are actually the modal behavior, the first 5 modes of the robot. And typically, when people make robots, they make sure the first mode is up around the top single figures, up towards 10 hertz. The reason to do this is to make the controls of walking easier. It's very difficult to walk if you can't guarantee where your foot is wobbling around. That's okay if you make one robot. We want to make thousands, maybe millions. We haven't got the luxury of making them from carbon fiber and titanium. We want to make them from plastic. Things are not quite so stiff. So we can't have these high targets. I call them dumb targets. We've got to make them work at lower targets. So is that going to work? Well, if you think about it, sorry about this, but we're just bags of soggy jelly and bones thrown in. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. It just makes controls harder. So we take the information from this, the modal data and the stiffness, and feed that into the control system. That allows it to walk. Just changing tack slightly, looking at the knee. We can take some inspiration from biology, and we can look to see what the mechanical advantage of the knee is. It turns out it actually represents quite similar to 4-bar link, and that's quite non-linear. That's not surprising, really, because if you think when you bend your leg down, the torque on your knee is much more when it's bent than it is when it's straight. So you'd expect a non-linear function. And in fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks through this graph, and this is showing picking things up, walking, squatting, the tasks I said we did on the stress. And that's the the torque seen at the knee against the knee bend on the horizontal axis. This is showing the requirement for the knee to do all these tasks. I've then put a curve through it, surfing over the top of the peaks, and that's saying this is what's required to make the robot do these tasks. So if we look at the 4-bar link, that's actually the green curve, and it's saying that the non-linearity of the 4-bar link has actually linearized the characteristic of the force. What that really says is that's lowered the force. That's what makes the actuator have the lowest possible force, which is the most efficient. We want to burn energy up slowly. What's the blue curve? Well, the blue curve is actually if we didn't have a 4-bar link, we just had an arm sticking out of my leg here with an actuator on it, a simple 2-bar link. That's the best we could do with a simple 2-bar link. And it shows that that would create much more force in the actuator, which would not be efficient. So what's that look like in practice? Well, as you'll see, it's very tightly packaged in the knee. You'll see it go transparent in a second. You'll see the 4-bar link there. It's operating on the actuator. This is determining the force and the displacements on the actuator. I'll now pass you over to Konstantinos, who'll tell you a lot more detail about how these actuators are made and designed and optimized. Thank you.
Thank you, Malcolm. So I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay it over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a simple point into the cloud. Then we do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for our optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize. And we parse our cloud. We parse our cloud, again, for every joint spec. And the red axis this time denote the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs. And even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable, we need to be able to reduce the amount of unique actuator designs. Therefore, we run something called Commonality Study, which we parse our cloud again, looking this time for actuators that simultaneously meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map at the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side angular contact ball bearing, and on the high-speed side and on the low-speed side a cross-roller bearing, and the gear train is a strain wave gear. There are 3 integrated sensors here and a bespoke permanent magnet machine. The linear actuator The linear actuator has planetary rollers and an inverted planetary screw as a gear train, which allows efficiency and compaction and durability. So in order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. And I will let you enjoy the video. So our actuator is able to lift a half-ton, 9-foot concert grand piano. And this is a requirement. It's not something nice to have, because our muscles can do the same when they are direct driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague, Mike, who's going to talk to you about hand design. Thank you very much.
Thanks, Konstantinos. So we just saw how powerful a human and a humanoid actuator can be. However, humans are also incredibly dexterous. The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors, and it has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting, because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors. You just heard how we went about designing the TeslaBot hardware. Now I'll hand it off to Milan and our autonomy team to bring this robot to life.
Thanks, Mike. All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work that we've done on Autopilot over the past few years. Most of those components ported quite easily over to the bot's environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. Another interesting problem to think about is, in indoor environments, mostly with absence of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. We also did quite some work on the simulation side, and this is literally the Autopilot Simulator, to which we've integrated the robot's locomotion code. And this is a video of the motion control code running in the Autopilot Simulator, showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months. And so locomotion is specifically one component that's very different as we're moving from the car to the bot's environment. And so I think it warrants a little bit more depth, and I'd like my colleagues to start talking about this now.
Thank you, Milan. Hi, everyone. I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And in the following, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bot, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then foot trajectories that connect these footsteps using toe-off and heel strike just as humans do. And this gives us a larger stride and less knee bend for higher efficiency of the system. The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Thank you, Felix. Hello, everyone. My name is Anand, and I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens. It takes a couple steps and falls down. Well, that's a little disappointing. But we are missing a few key pieces here, which will make it walk. Now, as Felix mentioned, the motion planner is using an idealized version of itself and a version of reality around it. This is not exactly correct. It also expresses its intention through trajectories and wrenches. Wrenches are forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planet doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model, we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Hi, everyone. My name is Eric, robotics engineer on TeslaBot, and I want to talk about how we've made the robot manipulate things in the real world. We wanted to manipulate objects while looking as natural as possible, and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead. Next, Milan's going to talk about what's next for the Optimus, Tesla bot. Thanks.
Thanks, Eric. Right, so hopefully by now you guys got a good idea of what we've been up to over the past few months. We started having something that's usable, but it's far from being useful. There's still a long and exciting road ahead of us. I think the first thing within the next few weeks is to get Optimus at least at par with Bumblebee, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories, and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I was mentioning earlier, indoor navigation, graceful fall management, or even servicing, all components needed to scale this product up. But I don't know about you, but after seeing what we've shown tonight, I'm pretty sure we can get this done within the next few months or years and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.
Hey, everyone. Hi, I'm Ashok. I lead the Autopilot team alongside Milan. God, it's going to be so hard to top that Optimus section. We'll try nonetheless. Anyway, every Tesla that has been built over the last several years, we think has the hardware to make the car drive itself. We have been working on the software to add higher and higher levels of autonomy. This time around last year, we had roughly 2,000 cars driving our FSD beta software. Since then, we have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today. Thank you. This did not come for free. It came from the sweat and blood of the engineering team over the last 1 year. For example, we trained 75,000 neural network models just last 1 year. That's roughly a model every 8 minutes. That's coming out of the team, and then we evaluate them on our large clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the stack. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD beta software is quite capable of driving the car. It should be able to navigate from parking lot to parking lot, handling city street driving, stopping for traffic lights and stop signs, negotiating with objects at intersections, making turns, and so on. All of this comes from the camera streams that go through our neural networks that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car, and the planning software drives the car based on that. Today, we'll go into a lot of the components that make up the system. The Occupancy Network acts as the base geometry layer of the system. This is a multi-camera video neural network that, from the images, predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts. If it's physically present, it predicts them, along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course. But then the roadways have lots of different lanes, and they connect in all kinds of ways. So it's actually a really difficult problem for typical computer vision techniques to predict the set of lanes and their connectivities. So we reached all the way into language technologies and then pulled the state of the art from other domains, and not just computer vision, to make this task possible. For vehicles, we need their full kinematic state to control for them. All of this directly comes from neural networks. Video streams, raw video streams, come into the networks, go through a lot of processing, and then outputs the full kinematic state. The positions, velocities, acceleration, jerk, all of that directly comes out of the networks with minimal post-processing. That's really fascinating to me, because how is this even possible? What world do we live in that this magic is possible, that these networks predicts fourth derivatives of these positions, when people thought we couldn't even detect these objects? My opinion is that it did not come for free. It required tons of data, so we had to build sophisticated auto-labeling systems that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks, distill the information into labels that train our in-car neural networks. On top of this, we also use our simulation system to synthetically create images. And since it's a simulation, we trivially have all the labels. All of this goes through a well-oiled data engine pipeline, where we first train a baseline model with some data, ship it to the car, see what the failures are. And once we know the failures, we mine the fleet for the cases where it fails, provide the correct labels, and add the data to the training set. This process systematically fixes the issues. And we do this for every task that runs in the car.
Yeah, and to train these new massive neural networks, this year we expanded our training infrastructure by roughly 40 to 50%. So that sits us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks and map them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent system on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we had to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced scheduling code across the full FSD platform.
All of these neural networks running in the car together produce the vector space, which is again the model of the world around the robot or the car. And then the planning system operates on top of this, coming up with trajectories that avoid collisions or smooth, make progress towards the destination using a combination of model-based optimization plus neural network that helps optimize it to be really fast. Today, we are really excited to present progress on all of these areas. We have the engineering leads standing by to come in and explain these various blocks. And these power not just the car, but the same components also run on the Optimus robot that Milan showed earlier. With that, I welcome Paril to start talking about the planning section.
Hi all, I'm Paril Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. So a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal and lateral profile. Now, obviously, we are being a jerk to the pedestrian, and we would spook the pedestrian and his cute pet. We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing: stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents pass. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far, because you will miss out on a lot of valid interactions. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem. It will be close to order of 10 milliseconds, even after a lot of incremental approximations. Now, for a typical crowded, unprotected lift, say you have more than 20 objects, each object having multiple different future modes, the number of relevant interaction combinations will blow up. The planner needs to make a decision every 50 milliseconds. So how do we solve this in real time? We rely on a framework what we call as interaction search, which is basically a parallelized tree search over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, their nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting. We use a set of maneuver trajectory candidates to branch over a bunch of interaction decisions, and also incremental goals for a longer horizon maneuver. Let's walk through this tree search very quickly to get a sense of how it works. We start with a set of vision measurements, namely lanes, occupancy, moving objects. These get represented as sparse abstractions as well as latent features. we use this to create a set of goal candidates, lanes again from the lanes network, or unstructured regions which correspond to a probability mask derived from human demonstrations. Once we have a bunch of these goal candidates, we create seed trajectories using a combination of classical optimization approaches, as well as our network planner, again trained on data from the customer fleet. Now, once we get a bunch of these seed trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized. So we branch further onto the option on the right, and that's where we bring in more and more complex interactions, building this optimization problem incrementally with more and more constraints. And the tree search keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the tree search. Inside each node, initially we started with creating trajectories using classical optimization approaches, where the constraints, like I described, would be added incrementally. And this would take close to 1 to 5 milliseconds per action. Now, even though this is a fairly good number, when you want to evaluate more than 100+ interactions, this does not scale. So we ended up building lightweight queryable networks that you can run in the loop of the planner. These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits. With this, we were able to bring the runtime down to close to 100 microseconds per action. Now, doing this alone is not enough, because you still have this massive tree search that you need to go through, and you need to efficiently prune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis, what is the jerk and axle required for a given maneuver. The customer fleet data plays an important role here again. We run 2 sets of, again, lightweight queryable networks, both really augmenting each other. One of them trained from interventions from the FST beta fleet, which gives a score on how likely is a given maneuver to result in interventions over the next few seconds. And second, which is purely on human demonstrations, human-driven data, giving a score on how close is your given selected action to a human-driven trajectory. The scoring helps us prune the search space, keep branching further on the interactions, and focus the compute on the most promising outcomes. The cool part about this architecture is that it allows us to create a cool blend between data-driven approaches, where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks. Now, a lot of what I described was with respect to the agents we could observe in the scene, but the same framework extends to objects behind occlusions. We use the video feed from 8 cameras to generate the 3D occupancy of the world. The blue mask here corresponds to the visibility region, we call it. It basically gets blocked at the first occlusion you see in the scene. We consume this visibility mask to generate what we call as ghost objects, which you can see on the top left. Now, if you model the spawn regions and the state transitions of these ghost objects correctly, if you tune your control response as a function of their existence likelihood, you can extract some really nice human-like behaviors. Now, I'll pass it on to Phil to describe more on how we generate these occupancy networks. Thank you.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year. This network is our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. And what you will see here is the raw network output from our internal dev tool. The occupancy network takes video streams of all our 8 cameras as input, produces a single unified volumetric occupancy in vector space directly. For every 3D location around our car, it predicts the probability of that location being occupied or not. Since it has video context, it is capable of predicting obstacles that are occluded instantaneously. For each location, it also produces a set of semantics such as curb, car, pedestrian, and road debris, as color-coded here. Occupancy flow is also predicted for motion. Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motions, such as a swerving trainer here. This network is currently running in all Teslas with FSD computers, and it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator. So how does this work? Let's take a look at the architecture. First, we rectify each camera images with the camera calibration. And the images we're showing here were given to the network. It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count image to the network. Since it has 4 bits more information, it has 16 times better dynamic range, as well as reduced latency, since we don't have to run ISP in the loop anymore. We use a set of reglets and FPNs as a backbone to extract image space features. Next, we construct a set of 3D position query along with the image space features as keys and values fit into an attention module. The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry to derive motion. Next, these spatial temporal features go through a set of deconvolution to produce the final occupancy and occupancy flow output. They're formed as fixed-size voxel grid, which might not be precise enough for planning and control. In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location. After knowing the model better, let's take a look at another example. Here, we have an articulated bus parked on the right side of the road, highlighted as an L-shaped voxel here. As we approach, the bus starts to move. The front of the car turns blue first, indicating the model predicts the front of the bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated problem for traditional object detection network, as you have to see whether I'm going to use one cuboid or perhaps 2 to fit the curvature. But for our occupancy network, since all we care about is the occupancy in the visible space, and we'll be able to model the curvature precisely. Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads. The surface and the voxel grid are not predicted independently. Instead, the voxel grid actually aligns with the surface implicitly. Here, we're at a hill crest where you can see the 3D geometry of the surface being predicted nicely. Planner can use this information to decide perhaps we need to slow down more for the hill crest. And as you can also see, the voxel grid aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field, or NeRF. We're looking into both incorporate some of the nice NeRF features into occupancy network training, as well as using our network output as the input state for NeRF. As a matter of fact, Ashok is very excited about this. This has been his personal weekend project for a while.
About these NeRFs, because I think the academia is building a lot of these foundation models for language, using like tons of large data sets for language. But I think for vision, NeRFs are going to provide the foundation models for computer vision, because they are grounded in geometry, and geometry gives us a nice way to supervise these networks and frees us of the requirement to define an ontology. And the supervision is essentially free because you just have to differentially render these images. So I think in the future, this occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentiably rendered into any image that was observed. I personally think is a future of computer vision, and we do some initial work on it right now, but I think in the future, both at Tesla and in the academia, we will see that these combination of one-shot prediction of full volumetric occupancy will be the future. That's my personal bet.
Thanks, Ashok. So here's an example early result of a 3D reconstruction from our fleet data. Instead of focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the world in 3D space for driving. And we want to do this for all our fleet data all over the world in all weather and lighting conditions. And obviously, this is a very challenging problem, and we're looking for you guys to help. Finally, the occupancy network is trained with large auto-label dataset without any human in the loop. And with that, I'll pass to Tim to talk about what it takes to train this network.
Thanks, Phil. All right, hey everyone. Let's talk about some training infrastructure. So we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips than that. So we've been looking at the occupancy networks just from Phil. Just Phil's videos, it takes 1.4 billion frames to train that network, what you just saw. And if you have 100,000 GPUs, it would take 1 hour. But if you have 1 GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and around 4,000 GPUs for auto-labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache. You shouldn't think of our data sets as fixed, let's say, as you think of your ImageNet or something, with like 1 million frames. You should think of it as a very fluid thing. So we've got 500,000 of these videos flowing in and out of these clusters every single day. And we track 400,000 of these kind of Python video instantiations every second. So that's a lot of calls. We're going to need to capture that in order to govern the retention policies of this distributed video cache. So underlying all of this is a huge amount of infra, all of which we build and manage in-house. So you cannot just buy 14,000 GPUs and then 30 petabytes of flash NVMe and just put it together and let's go train. It actually takes a lot of work, and I'm going to go into a little bit of that. What you actually typically want to do is you want to take your accelerator, so that could be the GPU or Dojo, which we'll talk about later, and because that's the most expensive component, that's where you want to put your bottleneck. And so that means that every single part of your system is going to need to outperform this accelerator. And so that is really complicated. That means that your storage is going to need to have the size and the bandwidth to deliver all the data down into the nodes. These nodes need to have the right amount of CPU and memory capabilities to feed into your machine learning framework. This machine learning framework then needs to hand it off to your GPU, and then you can start training. But then you need to do so across hundreds or thousands of GPU in a reliable way, in lockstep, and in a way that's also fast. So you're also going to need an interconnect. Extremely complicated. We'll talk more about Dojo in a second. So first, I want to take you through some optimizations that we've done on our cluster. So we're getting in a lot of videos, and video is very much unlike, let's say, training on images or text, which I think is very well established. Video is quite literally a dimension more complicated. And so that's why we needed to go end-to-end from the storage layer down to the accelerator and optimize every single piece of that. Because we train on the photon count videos that come directly from our fleet, we train on those directly. We do not post-process those at all. The way it's just done is we seek exactly to the frames we select for our batch. We load those in, including the frames that they depend on. So these are your iframes or your key frames. We package those up, move them into shared memory, move them into a double buffer on the GPU, and then use the hardware decoder that's only accelerated to actually decode the video. So we do that on the GPU natively. And this is all in a very nice PyTorch extension. Doing so unlocked more than 30% training speed increase for the occupancy networks and freed up basically the whole CPU to do any other thing. You cannot just do training with just videos. Of course, you need some kind of a ground truth. And that is actually an interesting problem as well. The objective for storing your ground truth is that you want to make sure you get to your ground truth that you need in the minimal amount of file system operations and load in the minimal size of what you need in order to optimize for aggregate cross-cluster throughput, because you should see a compute cluster as one big device which has internally fixed constraints and thresholds. So for this, we rolled out a format that is native to us that's called small. We use this for our ground truth, our feature cache, and any inference outputs. So a lot of tensors that are in there. And so just a cartoon here, let's say these are is your table that you want to store, then that's how that would look out if you rolled out on disk. So what you do is you take anything you'd want to index on, so for example, video timestamps, you put those all in the header, so that in your initial header read, you know exactly where to go on disk. Then if you have any tensors, you're going to try to transpose the dimensions to put a different dimension last as the contiguous dimension, and then also try different types of compression. Then you check out which one was most optimal, and then store that one. This is actually a huge tip if you do feature caching. Unintelligible output from the machine learning network, rotate around the dimensions a little bit, you can get up to 20% increase in efficiency of storage. Then when you store that, we also order the columns by size so that all your small columns and small values are together, so that when you seek for a single value, you're likely to overlap with the read on more values, which you'll use later, so that you don't need to do another file system operation. So I could go on and on. I just went on, touched on 2 projects that we have internally, but this is actually part of a huge continuous effort to optimize the compute that we have in-house. So accumulating and aggregating through all these optimizations, we now train our occupancy networks twice as fast just because it's twice as efficient. And now if we add in a bunch more compute and go parallel, we can now train this in hours instead of days. And with that, I'd like to hand it off to the biggest user of compute, John.
Hi, everybody. My name is John Emmons. I lead the Autopilot vision team. I'm going to cover 2 topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection problem as an image space instance segmentation task. Our network was super simple, though. In fact, it was only capable of predicting lanes of a few different kinds of geometries. Specifically, it would segment the eagle lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today we're trying to build a system that's capable of much more complex maneuvers. Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down. Taking a step back for a moment, what we're trying to do here is to predict the sparse set of lane instances and their connectivity. And what we want to do is to have a neural network that basically predicts this graph, where the nodes are the lane segments, and the edges encode the connectivities between these lanes. So what we have is our lane detection neural network. It's made up of 3 components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers that encode the video streams from our 8 cameras on the vehicle and produce a rich visual representation. We then enhance this visual representation with a coarse road-level map data, which we encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first 2 components here produce a dense tensor that sort of encodes the world, but what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities. In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers on the tokens encode the connective relationships between these lanes. By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally. I'm now going to dive into a little bit more detail of this language component. What I have depicted on the screen here is a satellite image which sort of represents the local area around the vehicle. The set of nodes and edges is what we refer to as the lane graph, and it's ultimately what we want to come out of this neural network. We start with a blank slate. We're going to want to make our first prediction here at this green dot. This green dot's position is encoded as an index into a coarse grid which discretizes the 3D world. Now, we don't predict this index directly because it would be too computationally expensive to do so. There's just too many grid points, and predicting a categorical distribution over this has both implications at training time and test time. So instead, what we do is we discretize the world coarsely first. We predict a heat map over the possible locations, and then we latch in the most probable location. Condition on this, we then refine the prediction and get the precise point. Now, we know where the position of this token is, but we don't know its type. In this case, though, it's the beginning of a new lane. So we predict it as a start token. And because it's a start token, there's no additional attributes in our language. We then take the predictions from this first forward pass, and we encode them using a learned positional embedding, which produces a set of tensors that we combine together, which is actually the first word in our language of lanes. We add this to the first position in our sentence here. We then continue this process by predicting the next lane point in a similar fashion. Now, this lane point is not the beginning of a new lane. It's actually a continuation of the previous lane. So it's a continuation token type. Now, it's not enough just to know that this lane is connected to the previously predicted lane. We want to encode its precise geometry, which we do by regressing a set of spline coefficients. We then take this lane, we encode it again, and add it as the next word in the sentence. We continue predicting these continuation lanes until we get to the end of the prediction grid. We then move on to a different lane segment. So you can see that cyan dot there. Now, it's not topologically connected to that pink point. It's actually forking off of that green point there. So it's got a fork type. And fork tokens actually point back to previous tokens from which the fork originates. So you can see here the fork point predictor is actually the index 0. So it's actually referencing back to tokens that it's already predicted, like you would in language. We continue this process over and over again until we've enumerated all of the tokens in the lane graph. And then the network predicts the end of sentence token.
Yeah, I just want to note that the reason we do this is not just because we want to build something complicated. It almost feels like a Turing-complete machine here with neural networks, though, is that we tried simpler approaches. For example, trying to just segment the lanes along the road or something like that. But then the problem is when there's uncertainty. Say you cannot see the road clearly, and there could be 2 lanes or 3 lanes, and you can't tell. A simple segmentation-based approach would just draw both of them. It's kind of a 2.5 lane situation. And the post-processing algorithm would hilariously fail when the predictions are such.
Yeah, and the problems don't end there. I mean, you need to predict these connective lanes inside of intersections, which it's just not possible with the approach that Ashok's mentioning, which is why we had to upgrade to this sort of.
Yeah, when it overlaps like this, segmentation would just go haywire. But even if you try very hard to put them on separate layers, it's just a really hard problem. But language just offers a really nice framework for getting a sample from a posterior as opposed to trying to do all of this in post-processing. But this doesn't actually stop for just Autopilot, right, John? This can be used for Optimus.
Yeah, I guess they wouldn't be called lanes, but you could imagine, sort of in this, stage here, that you might have sort of paths that sort of, encode the possible places that people could walk.
Yeah, it's basically if you're in a factory or in a home setting, you can just ask the robot, okay, please route to the kitchen, or please route to some location in the factory, and then we predict a set of pathways that would go through the aisles, take the robot, and say, okay, this is how you get to the kitchen. It just really gives us a nice framework to model these different paths that simplify the navigation problem for the downstream planner.
All right, so ultimately what we get from this lane detection network is a set of lanes and their connectivities, which comes directly from the network. There's no additional step here for sparsifying these dense predictions into sparse ones. This is just the direct, unfiltered output of the network. OK, so I talked a little bit about lanes. I'm going to briefly touch on how we model and predict the future paths and other semantics on objects. So I'm just going to go really quickly through 2 examples. The video on the right here, we've got a car that's actually running a red light and turning in front of us. What we do to handle situations like this is we predict a set of short time horizon future trajectories on all objects. We can use these to anticipate the dangerous situation here and apply whatever braking and steering actions required to avoid a collision. In the video on the right, there's 2 vehicles in front of us. The one in the left lane is parked. Apparently, it's being loaded, unloaded. I don't know why the driver decided to park there. But the important thing is that our neural network predicted that it was stopped, which is the red color there. The vehicle in the other lane, as you notice, also is stationary. But that one's obviously just waiting for that red light to turn green. So even though both objects are stationary and have 0 velocity, it's the semantics that is really important here so that we don't get stuck behind that awkwardly parked car. Predicting all of these agent attributes presents some practical problems when trying to build a real-time system. We need to maximize the frame rate of our object detection stack so that Autopilot can quickly react to the changing environment. Every millisecond really matters here. To minimize the inference latency, our neural network is split into 2 phases. In the first phase, we identify the locations in 3D space where agents exist. In the second stage, we then pull out tensors at those 3D locations, append it with additional data that's on the vehicle, and then we do the rest of the processing. This sparsification step allows the neural network to focus compute on the areas that matter most, which gives us superior performance for a fraction of the latency cost. So putting it all together, the Autopilot vision stack predicts more than just the geometry and kinematics of the world. It also predicts a rich set of semantics, which enables safe and human-like driving. I'm now going to hand things off to Sri, who will tell us how we run all these cool neural networks on our FSD computer. Thank you.
Hi everyone, I'm Sri. Today I'm going to give a glimpse of what it takes to run these FSD networks in the car and how do we optimize for the inference latency. Today I'm going to focus just on the FSD lanes network that John just talked about. So when we started this track, we wanted to know if we can run this FSD lanes network natively on the Trip engine, which is our in-house neural network accelerator that we built in the FSD computer. When we built this hardware, we kept it simple, and we made sure it can do one thing ridiculously fast: dense dot products. But this architecture is autoregressive and iterative, where it crunches through multiple attention blocks in the inner loop, producing sparse points directly at every step. So the challenge here was, how can we do this sparse point prediction and sparse computation on a dense dot product engine? Let's see how we did this on the Trip. So the network predicts the heat map of most probable spatial locations of the point. Now we do a argmax and a one-hot operation, which gives the one-hot encoding of the index of the spatial location. Now we need to select the embedding associated with this index from an embedding table that is learned during training. To do this on Trip, we actually built a lookup table in SRAM, and we engineered the dimensions of this embedding such that we could achieve all of this thing with just matrix multiplication. Not just that, we also wanted to store this embedding into a token cache so that we don't recompute this for every iteration, rather reuse it for future point prediction. Again, we pulled some tricks here where we did all these operations just on the dot product engine. It's actually cool that our team found creative ways to map all these operations on the Trip engine in ways that were not even imagined when this hardware was designed. But that's not the only thing we had to do to make this work. We actually implemented a whole lot of operations and features to make this model compilable, to improve the int8 accuracy, as well as to optimize performance. All of these things helped us run this 75 million parameter model just under 10 milliseconds of latency, consuming just 8 watts of power. But this is not the only architecture running in the car. There are so many other architectures modules, and networks we need to run in the car. To give a sense of scale, there are about a billion parameters of all the networks combined, producing around 1,000 neural network signals. So we need to make sure we optimize them jointly and such that we maximize the compute utilization, throughput, and minimize the latency. So we built a compiler just for neural networks that shares the structure to traditional compilers. As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker, which shares the structure to traditional linker, where we perform this link time optimization. There, we solve an offline optimization problem with compute memory and memory bandwidth constraints so that it comes with an optimized schedule that gets executed in the car. On the runtime, we designed a hybrid scheduling system which basically does heterogeneous scheduling on one SoC and distributed scheduling across both the SoCs to run these networks in a model parallel fashion. To get 100 TOPS of compute utilization, we need to optimize across all the layers of software, right from tuning the network architecture, the compiler, all the way to implementing a low latency, high bandwidth RDMA link across both the SoCs, and in fact, going even deeper to understanding and optimizing the cache coherent and non-coherent data paths of the accelerator in the SoC. This is a lot of optimization at every level in order to make sure we get the highest frame rate, and as every millisecond counts here. And this is just the visualization of the neural networks that are running in the car. This is our digital brain, essentially. As you can see, these operations are nothing but just the matrix multiplication, convolution, to name a few, real operations running in the car. To train this network with 1 billion parameters, you need a lot of labeled data. So Egan is going to talk about how do we achieve this with the auto labeling pipeline.
Thank you, Sri. Hi, everyone. I'm Yegan Zhang, and I'm leading geometric vision at Autopilot. So, yeah, let's talk about auto labeling. So we have several kinds of auto labeling frameworks to support various types of networks. But today, I'd like to focus on the awesome LanesNet here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more. So then how to do that? So it is certainly achievable to source sufficient amount of trips because we already have, as Tim explained earlier, we already have like 500,000 trips per day cache rate. However, converting all those data into a training form is a very challenging technical problem. To solve this challenge, we've tried various ways of manual and auto labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we want an even better auto labeling machine that can provide us good quality, diversity, and scalability. To meet all these requirements, despite the huge amount of engineering effort required here, we've developed a new auto labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling with just 12 hours on cluster for labeling 10,000 trips. So how we solved? There are 3 big steps. The first step is high precision trajectory and structure recovery by multi-camera, visual inertial odometry. So here, all the features, including ground surface, are inferred from videos by neural networks, then tracked and reconstructed in the vector space. So the typical drift rate of this trajectory in car is like 1.3 centimeter per meter and 0.45 milliradian per meter, which is pretty decent considering its compact compute requirement. Then the recovered surface and road details are also used as a strong guidance for the later manual verification step. This is also enabled in every FSD vehicle, so we get pre-processed trajectories and structures along with the trip data. The second step is multi-trip reconstruction, which is the big and core piece of this machine. So the video shows how the previously shown trip is reconstructed and aligned with other trips. Basically, other trips from different vehicles, not the same vehicle. So this is done by multiple internal steps like course alignment, pairwise matching, joint optimization, then further surface refinement. In the end, the human analyst comes in and finalizes the label. So each habit steps are already fully parallelized on the cluster. So the entire process usually takes just a couple of hours. The last step is actually auto-labeling the new trips. So here, we use the same multi-trip alignment engine, but only between pre-built reconstruction and each new trip. So it's much, much simpler than fully reconstructing all the clips altogether. That's why it only takes 30 minutes per trip to auto-label instead of several hours of manual labeling. And this is also the key of scalability of this machine. This machine easily scales as long as we have available compute and trip data. So about 50 trips were newly auto-labeled from this scene, and some of them are shown here. So 53 from different vehicles. So this is how we capture and transform the space-time slices of the world into the network supervision.
Yeah, one thing I'd like to note is that Jagan just talked about how we auto-label our lanes. But we have auto-labelers for almost every task that we do, including our planner. And many of these are fully automatic. There's no humans involved. For example, for objects, all of the kinematics, their shapes, their futures, everything just comes from auto-labeling. And the same is true for occupancy, too. And we have really just built a machine around this.
Yeah, so if you can go back one slide. One more. It says parallelized on cluster. So that sounds pretty straightforward, but it really wasn't. Maybe it's fun to share how something like this comes about. So a while ago, we didn't have any auto-labeling at all. And then someone makes a script. It starts to work. It starts working better until we reach a volume that's pretty high, and we clearly need a solution. And so there were two other engineers in our team who were like, hey, that's an interesting thing. What we needed to do was build a whole graph of essentially Python functions that would need to run one after the other. First, you pull the clip, then you do some cleaning, then you do some network inference, then another network inference, until you finally get this. So you need to do this at a large scale. So I tell them, we probably need to shoot for 100,000 clips per day, or like 100,000 items. That seems good. And so the engineer said, well, we can do a bit of Postgres and a bit of elbow grease. We can do it. Meanwhile, we are a bit later, and we're doing 20 million of these functions every single day. Again, we pull in around 500,000 clips, and on those, we run a ton of functions, each of these, in a streaming fashion. And so that's kind of the back-end infra that's also needed to not just run training, but also auto-labeling.
Yeah, it really is like a factory that produces labels, and like production lines, yield, quality, inventory, like all of the same concepts apply to this label factory. That applies for the factory for our cars.
That's right.
Okay, thanks, Tim and Ashok. So concluding this section, I'd like to share a few more challenging and interesting examples for network for sure, and even for humans probably. So from the top, there's like examples for like lack of lights case, or foggy night, or roundabout and heavy occlusions by parked cars, and even rainy night with the raindrops on camera lenses. These are challenging, but once their original scenes are fully reconstructed by other clips, all of them can be auto-labeled so that our cars can drive even better through these challenging scenarios. So now, let me pass the mic to David to learn more about how Sim is creating the new world on top of these labels. Thank you.
Thank you, Jagan. My name is David, and I'm going to talk about simulation. So simulation plays a critical role in providing data that is difficult to source and/or hard to label. However, 3D scenes are notoriously slow to produce. Take, for example, the simulated scene playing behind me, a complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete. And for us, that is painfully slow. However, I'm going to talk about using Yagen's automated ground truth labels along with some brand new tooling that allows us to procedurally generate this scene and many like it in just 5 minutes. That's an amazing 1,000 times faster than before. So let's dive in to how a scene like this is created. We start by piping the automated ground truth labels into our simulated world creator tooling inside the software Houdini. Starting with road boundary labels, we can generate a solid road mesh and retopologize it with the lane graph labels. This helps inform important road details like crossroad slope and detailed material blending. Next, we can use the line data and sweep geometry across its surface and project it to the road, creating lane paint decals. Next, using median edges, we can spawn island geometry and populate it with randomized foliage. This drastically changes the visibility of the scene. Now, the outside world can be generated through a series of randomized heuristics. Modular building generators create visual obstructions, while randomly placed objects like hydrants can change the color of the curbs, while trees can drop leaves below it, obscuring lines or edges. Next, we can bring in map data to inform positions of things like traffic lights or stop signs. We can trace along its normal to collect important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph, we can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations inside our simulator. And again, this is all automatic, no artist in the loop, and happens within minutes. And now this sets us up to do some pretty cool things. Since everything is based on data and heuristics, we can start to fuzz parameters to create visual variations of the single ground truth. It can be as subtle as object placement and random material swapping to more drastic changes like entirely new biomes or locations of environment, like urban, suburban, or rural. This allows us to create infinite, targeted permutations for specific ground truths that we need more ground truth for. And all this happens within a click of a button. And we can even take this one step further by altering our ground truth itself. Say John wants his network to pay more attention to the directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally alter our lane graph inside the simulator to help create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data that could never be collected from the real world. And the true power of this tool is in its architecture and how we can run all tasks in parallel to infinitely scale. So you saw the tile creator tool in action, converting the ground truth labels into their counterparts. Next, we can use our tile extractor tool to divide this data into geohash tiles about 150 meters square in size. We then save out that data into separate geometry and instance files. This gives us a clean source of data that's easy to load and allows us to be rendering engine agnostic for the future. Then, using a tile loader tool, we can summon any number of those cache tiles using a geohash ID. Currently, we're doing about these 5x5 tiles or 3x3, usually centered around fleet hotspots or interesting lane graph locations. And the tile loader also converts these tile sets into U assets for consumption by the Unreal Engine and gives you a finished product from what you saw in the first slide. And this really sets us up for size and scale. And as you can see on the map behind us, we can easily generate most of San Francisco city streets. And this didn't take years or even months of work, but rather 2 weeks by one person. And we can continue to manage and grow all this data using our PDG network inside of the tooling. This allows us to throw compute at it and regenerate all these tile sets overnight. This ensures all environments are of consistent quality and features, which is super important for training, since new ontologies and signals are constantly released. And now, to come full circle, because we generated all these tile sets from ground truth data, they contain all the weird intricacies from the real world, and we can combine that with the procedural, visual, and traffic variety to create limitless, targeted data for the network to learn from. And that concludes the sim section. I'll pass it to Kate to talk about how we can use all this data to improve Autopilot. Thank you.
Thanks, David. Hi, everyone. My name is Kate Park, and I'm here to talk about the data engine, which is the process by which we improve our neural networks via data. We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, Autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic, and thus a vehicle that we would slow down for. In reality, there's nobody in the car. It's just awkwardly parked. We've built this tooling to identify the mispredictions, correct the label, and categorize this clip into an evaluation set. This particular clip happens to be one of 126 that we've diagnosed as challenging parked cars at turns. Because of this infra, we can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fix 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge case, namely these parked cars at turns. But there are many challenge cases even for one signal of vehicle movement. We apply this data engine loop to every single challenge case we've diagnosed, whether it's buses, curvy roads, stopped vehicles, parking lots. And we don't just add data once, we do this again and again to perfect the semantic. In fact, this year, we updated our vehicle movement signal 5 times, and with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an online model. And Tesla's able to do this at scale because of the fleet advantage, the infra that our eng team has built, and the labeling resources that feed our networks. To train on all this data, we need a massive amount of compute, so I'll hand it off to Pete and Ganesh to talk about the Dojo supercomputing platform. Thank you.
Thank you, Katie. Thanks, everybody. Thanks for hanging in there. We're almost there. My name is Pete Bannon. I run the custom silicon and low voltage teams at Tesla.
And my name is Ganesh Venkat. I run the Dojo program.
Thank you. I'm frequently asked, why is a car company building a supercomputer for training? And this question fundamentally misunderstands the nature of Tesla. At its heart, Tesla is a hardcore technology company. All across the company, people are working hard in science and engineering to advance the fundamental understanding and methods that we have available to build cars, energy solutions, robots, and anything else that we can do to improve the human condition around the world. It's a super exciting thing to be a part of. and it's a privilege to run a very small piece of it in the semiconductor group. Tonight we're going to talk a little bit about Dojo and give you an update on what we've been able to do over the last year. But before we do that, I wanted to give a little bit of background on the initial design that we started a few years ago. When we got started, the goal was to provide a substantial improvement to the training latency for our Autopilot team. Some of the largest neural networks they train today run for over a month, which inhibits their ability to rapidly explore alternatives and evaluate them. So, a 30x speed up would be really nice if we could provide it at a cost competitive and energy competitive way. To do that, we wanted to build a chip with a lot of arithmetic units that we could utilize at a very high efficiency. And we spent a lot of time studying whether we could do that using DRAM, various packaging ideas, all of which failed. And in the end, even though it felt like an unnatural act, we decided to reject DRAM as the primary storage medium for this system and instead focus on SRAM embedded in the chip. SRAM provides, unfortunately, a modest amount of capacity, but extremely high bandwidth and very low latency. And that enables us to achieve high utilization with the arithmetic units. Those choices, that particular choice led to a whole bunch of other choices. For example, if you want to have virtual memory, you need page tables. They take up a lot of space. We didn't have space, so no virtual memory. We also don't have interrupts. The accelerator is a bare bones, raw piece of hardware that's presented to a compiler, and the compiler is responsible for scheduling everything that happens in a deterministic way. So there's no need or even desire for interrupts in the system. We also chose to pursue model parallelism as a training methodology, which is not the typical situation. Most machines today use data parallelism, which consumes additional memory capacity, which we obviously don't have. So all of those choices led us to build a machine that is pretty radically different from what's available today. We also had a whole bunch of other goals. One of the most important ones was no limits. So we wanted to build a compute fabric that would scale in an unbounded way for the most part. I mean, obviously there's physical limits now and then, but pretty much if your model was too big for the computer, you just had to go buy a bigger computer. That's what we were looking for. Today, the way machines are packaged, there's a pretty fixed ratio of, for example, GPUs, CPUs, and DRAM capacity and network capacity. And we really wanted to disaggregate all that so that as models evolved, we could vary the ratios of those various elements and make the system more flexible to meet the needs of the Autopilot team.
Yeah, and it's so true, Pete, like no limits philosophy was our guiding star all the way. All of our choices were centered around that. And to the point that we didn't want traditional data center infrastructure to limit our capacity to execute these programs at speed. So that's why we, sorry about that. That's why we integrated vertically our data center, the entire data center. By doing a vertical integration of the data center, we could extract new levels of efficiency. We could optimize power delivery, cooling, and as well as system management across the whole data center stack, rather than doing box by box and integrating those boxes into data centers. And to do this, we also wanted to integrate early to figure out limits of scale for our software workloads. So we integrated Dojo environment into our Autopilot software very early, and we learned a lot of lessons. And today, Bill Chang will go over our hardware update, as well as some of the challenges that we faced along the way. And Rajiv Kurian will give you a glimpse of our compiler technology, as well as go over some of our cool results.
Great. There you go.
Thanks, Pete. Thanks, Ganesh. I'll start tonight with a high-level vision of our system that'll help set the stage for the challenges and the problems we're solving, and then also how software will then leverage this for performance. Now, our vision for Dojo is to build a single unified accelerator, a very large one. Software would see a seamless compute plane with globally addressable, very fast memory, and all connected together with uniform, high bandwidth, and low latency. Now, to realize this, we need to use density to achieve performance. Now, we leverage technology to get this density in order to break levels of hierarchy all the way from the chip to the scale-out systems. Now, silicon technology has done this for decades. Chips have followed Moore's law for density and integration to get performance scaling. Now, a key step in realizing that vision was our training tile. Not only can we integrate 25 dies at extremely high bandwidth, but we can scale that to any number of additional tiles by just connecting them together. Now, last year, we showcased our first functional training tile. And at that time, we already had workloads running on it. And since then, the team here has been working hard and diligently to deploy this at scale. Now, we've made amazing progress and had a lot of milestones along the way. And of course, we've had a lot of unexpected challenges. But this is where our fail fast philosophy has allowed us to push our boundaries. Now, pushing density for performance presents all new challenges. One area is power delivery. Here, we need to deliver the power to our compute die, and this directly impacts our top-line compute performance. But we need to do this at unprecedented density. We need to be able to match our die pitch with a power density of almost 1 amp per millimeter squared. And because of the extreme integration, this needs to be a multi-tiered vertical power solution. And because there's a complex heterogeneous material stack-up, we have to carefully manage the material transition, especially CTE. Now, why does the coefficient of thermal expansion matter in this case? CTE is a fundamental material property. And if it's not carefully managed, that stack-up would literally rip itself apart. So we started this effort by working with vendors to develop this power solution. But we realized that we actually had to develop this in-house. Now, to balance schedule and risk, we built quick iterations to support both our system bring-up and software development, and also to find the optimal design and stack-up that would meet our final production goals. And in the end, we were able to reduce CTE over 50% and meet our performance by 3x over our initial version. Now, needless to say, finding this optimal material stack-up while maximizing performance at density is extremely difficult. Now, we did have unexpected challenges along the way. Here's an example where we pushed the boundaries of integration that led to component failures. This started when we scaled up to larger and longer workloads, and then intermittently, a single site on a tile would fail. Now, they started out as recoverable failures, but as we pushed to much higher and higher power, these would become permanent failures. Now, to understand this failure, you have to understand why and how we build our power modules. Solving density at every level is the cornerstone of actually achieving our system performance. Now, because our XY plane is used for high bandwidth communication, everything else must be stacked vertically. This means all other components other than our die must be integrated into our power modules. Now, that includes our clock and our power supplies and also our system controllers. Now, in this case, the failures were due to losing clock output from our oscillators. And after an extensive debug, we found that the root cause was due to vibrations on the module from piezoelectric effects on nearby capacitors. Now, singing caps are not a new phenomenon, and in fact, very common in power design. But normally, clock chips are placed in a very quiet area of the board, and often not affected by power circuits. But because we needed to achieve this level of integration, these oscillators need to be placed in very close proximity. Now, due to our switching frequency and then the vibration resonance created, it caused out-of-plane vibration on our MEMS oscillator that caused it to crack. Now, the solution to this problem is a multi-prong approach. We can reduce the vibration by using soft terminal caps. We can update our MEMS part with a lower Q factor for the out-of-plane direction. And we can also update our switching frequency to push the resonance further away from these sensitive bands. Now, in addition to the density at the system level, we've been making a lot of progress at the infrastructure level. We knew that we had to re-examine every aspect of the data center infrastructure in order to support our unprecedented power and cooling density. We brought in a fully custom designed CDU to support Dojo's dense cooling requirements. And the amazing part is we're able to do this at a fraction of the cost versus buying off the shelf and modifying it. And since our Dojo cabinet integrates enough power and cooling to match an entire row of standard IT racks, we need to carefully design our cabinet and infrastructure together. And we've already gone through several iterations of this cabinet to optimize this. And earlier this year, we started load testing our power and cooling infrastructure. And we were able to push it over 2 megawatts before we tripped our substation and got a call from the city. Yeah. Now, last year, we introduced only a couple of components of our system, the custom D1 die and the training tile. But we teased the exapod as our end goal. We'll walk through the remaining parts of our system that are required to build out this exapod. Now, the system tray is a key part of realizing our vision of a single accelerator. It enables us to seamlessly connect tiles together, not only within the cabinet, but between cabinets. We can connect these tiles at very tight spacing across the entire accelerator, and this is how we achieve our uniform communication. This is a laminated bus bar that allows us to integrate very high power, mechanical and thermal support, and an extremely dense integration. It's 75 millimeters in height and supports 6 tiles at 135 kilograms. This is the equivalent of 3 to 4 fully loaded high-performance racks. Next, we need to feed data to the training tiles. This is where we've developed the Dojo interface processor. It provides our system with high bandwidth DRAM to stage our training data. And it provides full memory bandwidth to our training tiles using TTP, our custom protocol that we use to communicate across our entire accelerator. It also has high-speed Ethernet that helps us extend this custom protocol over standard Ethernet. And we provide native hardware support for this with little to no software overhead. And lastly, we can connect to it through a standard Gen 4 PCIe interface. Now, we pair 20 of these cards per tray, and that gives us 640 gigabytes of high bandwidth DRAM. And this provides our disaggregated memory layer for our training tiles. These cards are our high bandwidth ingest path, both through PCIe and Ethernet. They also provide a high-radix Z connectivity path that allows shortcuts across our large Dojo accelerator. Now, we actually integrate the host directly underneath our system tray. These hosts provide our ingest processing and connect to our interface processors through PCIe. These hosts can provide hardware video decoder support for video-based training. And our user applications land on these hosts so we can provide them with the standard x86 Linux environment. Now, we can put 2 of these assemblies into one cabinet and pair it with redundant power supplies that do direct conversion of 3-phase 480-volt AC power to 52-volt DC power. Now, by focusing on density at every level, we can realize the vision of a single accelerator. Now, starting with the uniform nodes on our custom D1 die, we can connect them together in our fully integrated training tile, and then finally, seamlessly connecting them across cabinet boundaries to form our Dojo accelerator. And altogether, we can house 2 full accelerators in our exapod for a combined 1 exaflop of ML compute. Now, altogether, this amount of technology and integration has only ever been done a couple of times in the history of compute. Next, we'll see how software can leverage this to accelerate their performance.
Thanks, Bill. My name is Rajiv, and I'm going to talk some numbers. So our software stack begins with the PyTorch extension that speaks to our commitment to run standard PyTorch models out of the box. We're going to talk more about our JIT compiler and the ingest pipeline that feeds the hardware with data. Abstractly, performance is TOPS times utilization times accelerator occupancy. We've seen how the hardware provides peak performance. It's the job of the compiler to extract utilization from the hardware while code is running on it. And it's the job of the ingest pipeline to make sure that data can be fed at a throughput high enough for the hardware to not ever starve. So let's talk about why communication-bound models are difficult to scale. But before that, let's look at why ResNet 50-like models are easier to scale. You start off with a single accelerator, run the forward and backward passes, followed by the optimizer. Then to scale this up, you run multiple copies of this on multiple accelerators. And while the gradients produced by the backward pass do need to be reduced, and this introduces some communication, this can be done pipeline with the backward pass. This setup scales fairly well, almost linearly. For models with much larger activations, we run into a problem as soon as we want to run the forward pass. The batch size that fits in a single accelerator is often smaller than the batch norm surface. So to get around this, researchers typically run this setup on multiple accelerators in sync batch norm mode. This introduces latency-bound communication to the critical path of the forward pass, and we already have a communication bottleneck. And while there are ways to get around this, they usually involve tedious manual work best suited for a compiler. And ultimately, there's no skirting around the fact that if your state does not fit in a single accelerator, you can be communication bound. And even with significant efforts from our ML engineers, we see such models don't scale linearly. The Dojo system was built to make such models work at high utilization. The high-density integration was built to not only accelerate the compute-bound portions of a model, but also the latency-bound portions, like a batch norm, or the bandwidth-bound portions, like a gradient all reduce or a parameter all gather. A slice of the Dojo mesh can be carved out to run any model. The only thing users need to do is to make the slice large enough to fit a batch norm surface for their particular model. After that, the partition presents itself as one large accelerator, freeing the users from having to worry about the internal details of execution. And it's the job of the compiler to maintain this abstraction. Fine-grained synchronization primitives and uniform low latency makes it easy to accelerate all forms of parallelism across integration boundaries. Tensors are usually stored sharded in SRAM and replicated just in time for layers execution. We depend on the high Dojo bandwidth to hide this replication time. Tensor replication and other data transfers are overlapped with compute, and the compiler can also recompute layers when it's profitable to do so. We expect most models to work out of the box. As an example, we took the recently released Stable Diffusion model and got it running on Dojo in minutes. Out of the box, the compiler was able to map it in a model parallel manner on 25 Dojo dies. Here are some pictures of a Cybertruck on Mars generated by Stable Diffusion running on Dojo. Looks like it still has some ways to go before matching the Tesla Design Studio team. So we've talked about how communication bottlenecks can hamper scalability. perhaps an acid test of a compiler and the underlying hardware is executing a cross-die batch norm layer. Like mentioned before, this can be a serial bottleneck. So the communication phase of a batch norm begins with nodes computing their local mean and standard deviations, then coordinating to reduce these values, then broadcasting these values back, and then they resume their work in parallel. So what would an ideal batch norm look like on 25 Dojo dies? Let's say the previous layer's activations are already split across dies. We would expect the 350 nodes on each die to coordinate and produce die local mean and standard deviation values. Ideally, these would get further reduced with the final value ending somewhere towards the middle of the tile. We would then hope to see a broadcast of this value radiating from the center. Let's see how the compiler actually executes a real batch norm operation across 25 dies. The communication trees were extracted from the compiler, and the timing is from a real hardware run. We're about to see 8,750 nodes on 25 dies coordinating to reduce and then broadcast the batch norm mean and standard deviation values. Die local reduction, followed by global reduction towards the middle of the tie, then the reduced value broadcast radiating from the middle, accelerated by the hardware's broadcast facility. This operation takes only 5 microseconds on 25 Dojo dies. The same operation takes 150 microseconds on 24 GPUs. This is an orders of magnitude improvement over GPUs. And while we talked about an all-reduce operation in the context of a batch norm, it's important to reiterate that the same advantages apply to all other communication primitives. And these primitives are essential for large-scale training. So how about full model performance? So while we think that the ResNet 50 is not a good representation of real-world Tesla workloads, it is a standard benchmark, so let's start there. We are already able to match the A100 die for die. However, perhaps a hint of Dojo's capabilities is that we're able to hit this number with just a batch of 8 per die. But Dojo was really built to tackle larger, complex models. So when we set out to tackle real-world workloads, we looked at the usage patterns of our current GPU cluster. And 2 models stood out: the auto-labeling networks, a class of offline models that are used to generate ground truth, and the occupancy networks that you heard about. The auto-labeling networks are large models that have high arithmetic intensity, while the occupancy networks can be ingest-bound. We chose these models because together they account for a large chunk of our current GPU cluster usage, and they would challenge the system in different ways. So how did we do on these 2 networks? The results we're about to see were measured on multi-die systems for both the GPU and Dojo, but normalized to per-die numbers. On our auto-labeling network, we're already able to surpass the performance of an A100 with our current hardware running on our older generation VRMs. On our production hardware with our newer VRMs, that translates to doubling the throughput of an A100. And our model showed that with some key compiler optimizations, we could get to more than 3x the performance of an A100. We see even bigger leaps on the occupancy network. Almost 3x with our production hardware, with room for more. So what does that mean for Tesla? With our current level of compiler performance, we could replace the ML compute of 1, 2, 3, 4, 5, and 6 GPU boxes with just a single Dojo tile. And this Dojo tile costs less than 1 of these GPU boxes.
Whoa.
What it really means is that networks that took more than a month to train now take less than a week. Alas, when we measured things, it did not turn out so well. At the PyTorch level, we did not see our expected performance out of the gate. And this timeline chart shows our problem. The teeny tiny little green bars, that's the compile code running on the accelerator. The row is mostly white space where the hardware is just waiting for data. With our dense ML compute, Dojo hosts effectively have 10x more ML compute than the GPU hosts. The data loaders running on this one host simply couldn't keep up with all that ML hardware. So to solve our data loader scalability issues, we knew we had to get over the limit of this single host. The Tesla Transport Protocol moves data seamlessly across host, tiles, and ingest processors. So we extended the Tesla Transport Protocol to work over Ethernet. We then built the Dojo network interface card, the DNIC, to leverage TTP over Ethernet. This allows any host with a DNIC card to be able to DMA to and from other TTP endpoints. So we started with the Dojo mesh. Then we added a tier of data loading hosts equipped with the DNIC card. We connected these hosts to the mesh via an Ethernet switch. Now every host in this data loading tier is capable of reaching all TTP endpoints in the Dojo mesh via hardware-accelerated DMA. After these optimizations went in, our occupancy went from 4% to 97%. So the data loading sections have reduced. The data loading sections have reduced drastically, and the ML hardware is kept busy. We actually expect this number to go to 100% pretty soon. After these changes went in, we saw the full expected speed up from the PyTorch layer, and we were back in business. So we started with hardware design that breaks through traditional integration boundaries in service of our vision of a single giant accelerator. We've seen how the compiler and ingest layers build on top of that hardware. So after proving our performance on these complex real-world networks, we knew what our first large-scale deployment would target, our high arithmetic intensity auto-labeling networks. Today, that occupies 4,000 GPUs over 72 GPU racks. With our dense compute and our high performance, we expect to provide the same throughput with just 4 Dojo cabinets. And these 4 Dojo cabinets will be part of our first exapod that we plan to build by Q1 of 2023. This will more than double Tesla's auto-labeling capacity. The first exapod is part of a total of 7 exapods that we plan to build in Palo Alto right here across the wall. And we have a display cabinet from one of these exapods for everyone to look at. 6 tiles densely packed on a tray, 54 petaflops of compute, 640 gigabytes of high bandwidth memory with power and host to feed it. A lot of compute. And we're building out new versions of all our cluster components and constantly improving our software to hit new limits of scale. We believe that we can get another 10x improvement with our next generation hardware. And to realize our ambitious goals, we need the best software and hardware engineers. So please come talk to us or visit tesla.com/AI. Thank you.
Let me know what
Okay. All right, so hopefully that was enough detail. And now we can move to questions. Guys, like I think the team can come out on stage, and but we really wanted to show the depth and breadth of Tesla in artificial intelligence, compute hardware, robotics, actuators, and try to really shift the perception of the company away from, a lot of people think we're like just a car company or we make cool cars, whatever, but they don't have, most people have no idea that Tesla is arguably the leader in real-world AI hardware and software. And that we're building what is arguably the first, the most radical computer architecture since the Cray 1 supercomputer. And I think if you're interested in developing some of the most advanced technology in the world that's going to really affect the world in a positive way, Tesla's the place to be. So yeah, let's fire away with some questions. I think there's a mic at the front and a mic at the back.
Chris,
or
on this side.
Just throw mics at people. Jump ball for the mic.
Yeah, hi, thank you very much. I was impressed here. Yeah. I was impressed very much by Optimus, but I wonder why tendon-driven, the hand? Why did you choose a tendon-driven approach for the hand? Because tendons are not very durable. And why spring-loaded?
Yeah. Hello, is this working? Cool, awesome. Yes, that's a great question. You know, when it comes to any type of actuation scheme, there's trade-offs between, you know, whether or not it's a tendon-driven system or some type of linkage-based system.
Just keep the mic close to your mouth.
A little bit closer.
Yeah.
Hear me? Cool. So yeah, the main reason why we went for a tendon-based system is that, you know, first we actually investigated some synthetic tendons, but we found that metallic Bowden cables are, you know, a lot stronger. One of the advantages of these cables is that it's very good for part reduction. We do want to make a lot of these hands, so having a bunch of parts, a bunch of small linkages ends up being, you know, a problem when you're making a lot of something. One of the big reasons that, you know, tendons are better than linkages in a sense is that you can be anti-backlash. So anti-backlash essentially, you know, allows you to not have any gaps or, you know, stuttery motion in your fingers. Spring-loaded, mainly what spring-loaded allows us to do is allows us to have active opening. So instead of having to have two actuators to drive the fingers closed and then open, we have the ability to, you know, have the tendon drive them closed and then the springs passively extend. And this is something that's seen in our hands as well, right? We have the ability to actively flex, and then we also have the ability to extend. Yeah.
I mean, our goal with Optimus is to have a robot that is maximally useful as quickly as possible. So there's a lot of ways to solve the various problems of a humanoid robot. We're probably not barking up the right tree on all the technical solutions. And I should say that we're open to evolving the technical solutions that you see here over time. They're not locked in stone. But we have to pick something, and we want to pick something that's going to allow us to produce the robot as quickly as possible and have it, like I said, be useful as quickly as possible. We're trying to follow the goal of fastest path to a useful robot that can be made at volume. And we're going to test the robot internally at Tesla in our factory. And just see, like, how useful is it? Because you have to have you've got to close the loop on reality to confirm that the robot is in fact useful. Yeah, so we're just going to use it to build things. And we're confident we can do that with the hand that we have currently designed. But for sure there'll be hand version 2, version 3, and we may change the architecture quite significantly over time.
The Optimus robot is really impressive. You did a great job. Bipedal robots are really difficult. But what I noticed might be missing from your plan is to acknowledge the utility of the human spirit, and I'm wondering if Optimus will ever get a personality and be able to laugh at our jokes while it folds our clothes.
Yeah, absolutely. I think we want to have really fun versions of Optimus, so that Optimus can both be utilitarian and do tasks, but can also be kind of like a friend and a buddy and hang out with you. And I'm sure people will think of all sorts of creative uses for this robot. You know, the thing, once you have the core intelligence and actuators figured out, then you can actually, you know, put all sorts of costumes, I guess, on the robot. I mean, you can make the robot look. You can skin the robot in many different ways, I'm sure people will find very interesting ways to versions of Optimus. So.
Thanks for the great presentation. I wanted to know if there was an equivalent to interventions in Optimus. It seems like labeling through moments where humans disagree with what's going on is important, and in a humanoid robot, that might be also a desirable source of information.
Want to say anything?
Yeah, I think we'll have ways to remote operate the robot and intervene when it does something bad, especially when we are training the robot and bringing it up. And hopefully we design it in a way that we can stop the robot from, if it's going to hit something, we can just like hold it and then it'll stop. It won't like crush your hand or something. And those are all intervention data. Yeah, and we can learn a lot from our simulation systems too, where we can check for collisions and supervise that those are bad actions.
Yeah, I mean, so Optimus, we want over time for it to be, an android, the kind of android that you'd seen in sci-fi movies, like Star Trek, The Next Generation, like Data. But obviously, we could program the robot to be less robot-like and more friendly, and it can obviously learn to emulate humans and feel very natural. So as AI in general improves, we can add that to the robot, and it should be obviously able to do simple instructions or even intuit what it is that you want. So you could give it a high-level instruction, and then it can break that down into a series of actions and take those actions.
Hi. Yeah, it's exciting to think that with the Optimus, you will think that you can achieve orders of magnitude of improvement in economic output. That's really exciting. And when Tesla started, the mission was to accelerate the advent of renewable energy or sustainable transport. So with the Optimus, do you still see that mission being the mission statement of Tesla, or is it going to be updated with, mission to accelerate the advent of, I don't know, infinite abundance or limitless economy?
Yeah, it is not strictly speaking, Optimus is not strictly speaking directly in line with accelerating sustainable energy. To the degree that it is more efficient at getting things done than a person, it does, I guess, help with sustainable energy. But I think the mission effectively does somewhat broaden with the advent of Optimus to I don't know, making the future awesome. So, I think you look at Optimus, and I don't know about you, but I'm excited to see what Optimus will become. And, this is like, if you could, you can tell, like any given technology, do you want to see what it's like in a year, 2 years, 3 years, 4 years, 5 years, 10? I'd say for sure. You definitely want to see what's happening with Optimus. Whereas, a bunch of other technologies are, sort of plateaued. Won't name names here, but so I think Optimus is going to be incredible in like 5 years, 10 years, like mind-blowing. And I'm really interested to see that happen, and I hope you are too.
I have a quick question here. I'm Justin, and I was wondering, are you planning to extend conversational capabilities for the robot? And my second follow-up question to that is, what's the end goal? What's the end goal with Optimus?
Yeah, Optimus would definitely have conversational capabilities. You'd be able to talk to it and have a conversation, and it would feel quite natural. So, from an end goal standpoint, I don't know. I think it's going to keep evolving, and I'm not sure where it ends up, but someplace interesting for sure. We always have to be careful about don't go down the Terminator path. That's I thought maybe we should start off with a video of the Terminator starting off with this, skull crushing, but that might be, people might take that too seriously. So, we do want Optimus to be safe, so we are designing in safeguards where you can locally stop the robot, and with like basically a localized control ROM that you can't update over the internet, which I think that's quite important, essential, frankly. So like a localized stop button, remote control, something like that, that cannot be changed. But I mean, it's definitely going to be interesting. It won't be boring. So.
Okay, yeah. I see you today. You have very attractive product with Dojo and its applications. So I'm wondering, what's the future for the Dojo platform? Will you provide infrastructure as service like AWS, or you will sell the chip like the NVIDIA? So basically, what's the future? Because I see you use 7 nanometer, so the development cost is easily over $10 million US. How do you make the business business-wise?
Yeah, I mean, Dojo is a very big computer, and actually will use a lot of power and need a lot of cooling. So I think it's probably going to make more sense to have Dojo operate in like a Amazon Web Services manner than to try to sell it to someone else. So that would be the most efficient way to operate Dojo, is just have it be a service that you can use that's available online, and that where you can train your models way faster and for less money. And as the world transitions to software 2.0,
and that's on the bingo card.
As someone I know has to now drink 5 tequilas. So let's see. Software 2.0
yeah.
will use a lot of neural net training. So it kind of makes sense that over time, as there's more neural net stuff, people will want to use the fastest, lowest cost neural net training system. So I think there's a lot of opportunity in that direction.
Hi, my name is Ali Jahanian. Thank you for this event. It's very inspirational. My question is, I'm wondering, what is your vision for humanoid robots that understand our emotions and art and can contribute to our creativity?
Well, I think you're already seeing robots that at least are able to generate very interesting art with like DALL-E and DALL-E 2. And I think we'll start seeing AI that can actually generate even movies that have coherence, like interesting movies and tell jokes. So it's quite remarkable how fast AI is advancing at many companies besides Tesla. We're headed for a very interesting future. And yeah, so you guys want to comment on that?
Yeah, I guess the Optimus robot can come up with physical art, not just digital art. You can ask for some dance moves in text or voice, and then you can produce those in the future. So it's a lot of physical art, not just digital art. Yeah.
Oh yeah. Computers can absolutely make physical art. Yeah. 100%.
Yeah, like dance, play soccer, or whatever you. I mean, it needs to get more agile, but over time, for sure.
Thanks so much for the presentation. For the Tesla Autopilot slides, I noticed that the models that you were using were heavily motivated by language models. And I was wondering what the history of that was and how much of an improvement it gave. I thought that was a really interesting, curious choice to use language models for the lane transitioning.
So there's sort of two aspects for why we transition to language modeling. So the first...
Talk loud and close.
Okay.
It's not coming through very clearly.
Okay, got it. Yeah, so the language models help us in two ways. The first way is that it lets us predict lanes that we couldn't have otherwise. As Ashok mentioned earlier, basically when we predicted lanes in sort of a dense 3D fashion, you can only model certain kinds of lanes, but we want to get those crisscrossing connections inside of intersections. It's just not possible to do that without making it a graph prediction. If you try to do this with dense segmentation, it just doesn't work. Also, the lane prediction is a multimodal problem. Sometimes you just don't have sufficient visual information to know precisely how things look on the other side of the intersection. So you need a method that can generalize and produce coherent predictions. You don't want to be predicting 2 lanes and 3 lanes at the same time. You want to commit to one, and a generative model like these language models provides that.
Hi. Hi. My name is Giovanni. Yeah, thanks for the presentation. It's really nice. I have a question for FSD team. So for the neural networks, how do you test, how do you do unit tests, software unit tests on that? Like, do you have like a bunch, or I don't know, maybe thousands or cases where the neural network that after you train it, you have to pass it before you release it as a product, right? What's your software unit testing strategies for this, basically?
Yeah, glad you asked. There's like a series of tests that we have defined, starting from unit tests for the software itself, but then for the neural network models, we have VAP sets defined where you can define. If you just have a large test set, that's not enough. What we find, we need like sophisticated VAP sets for different failure modes, and then we curate them and grow them over the time of the product. So over the years, we have like hundreds of thousands of examples where we have been failing in the past that we have curated. And so for any new model, we test against the entire history of these failures and then keep adding to this test set. On top of this, we have shadow modes where we ship these models in silent to the car, and we get data back on where they are failing or succeeding. And there's an extensive QA program. It's very hard to ship a regression. There's like 9 levels of filters before it hits customers, but then we have really good infra to make this all efficient.
And I'm one of the QA testers, so I QA the car.
Yeah,
like
QA tester.
Yeah, so I'm constantly in the car just being QAing like whatever the latest alpha build is that doesn't totally crash.
Yeah. Finds a lot of bugs.
Yeah.
Hi, great event. I have a question about foundational models for autonomous driving. We have all seen that big models that really can, when you scale up with data and model parameter, right, from GPT-3 to PaLM, it can actually now do reasoning. Do you see that is essential scaling up foundational models with data and size, and then at least you can get a teacher model, right, that potentially can solve all the problems, and then you distill to a student model. Is that how you see foundational models relevant for autonomous driving?
That's quite similar to our auto labeling model. So we don't just have models that run in the car. We train models that are entirely offline, that are like extremely large, that can't run in real time on the car. So we just run those offline on the servers, producing really good labels that can then train the online networks. So that's one form of distillation of these teacher-student models. In terms of foundation models, we are building some really, really large data sets that are multiple petabytes. And we are seeing that some of these tasks work really well when we have these large data sets. Like the kinematics, like I mentioned, video in, all the kinematics out of all the objects, and up to the 4th derivative. And people thought we couldn't do detection with cameras. I mean, detection, depth, velocity, acceleration. And imagine how precise these have to be for these higher order derivatives to be accurate. And this all comes from these kind of large data sets and large models. So we're seeing the equivalent of foundation models in our own way for geometry and kinematics and things like those. You want to add anything, John?
Yeah, I'll keep it brief. Basically, whenever we train on a larger data set, we see big... OK. Basically, whenever we train on a larger data set, we see big improvements in our model performance. And basically, whenever we initialize our networks with some pre-training step from some other auxiliary task, we basically see improvements. The self-supervised or supervised with large data sets both help a lot.
Hi. So at the beginning, Elon said that Tesla was potentially interested in building artificial general intelligence systems. Given the potentially transformative impact of a technology like that, it seems prudent to invest in technical AGI safety expertise specifically. I know Tesla does a lot of technical, narrow AI safety research. I was curious if Tesla was intending to try to build expertise in technical artificial general intelligence safety specifically.
Well, if we start looking like we're going to be making a significant contribution to artificial general intelligence, then we'll for sure invest in safety. I'm a big believer in AI safety. I think there should be an AI sort of regulatory authority at the government level, just as there is a regulatory authority for anything that affects public safety. So we have a regulatory authority for aircraft and cars and sort of food and drugs, and because they affect public safety. And AI also affects public safety. So I think, and this is not really something that government, I think, understands yet, but I think there should be a referee that is ensuring or trying to ensure public safety for AGI. And if you think of like, well, what are the elements that are necessary to create AGI? Like the accessible data set is extremely important, and if you've got a large number of cars and humanoid robots processing petabytes of video data and audio data from the real world, just like humans, that might be the biggest data set. It probably is the biggest data set. Because in addition to that, you can obviously incrementally scan the internet. But what the internet can't quite do is have millions or hundreds of millions of cameras in the real world, and with like I said, with audio and other sensors as well. So I think we probably will have the most amount of data, and probably the most amount of training power. Therefore, probably we will make a contribution to AGI.
Hey, I noticed the semi was back there, but we haven't talked about it too much. I was just wondering, for the semi-truck, what are the changes you're thinking about from a sensing perspective? I imagine there's very different requirements, obviously, than just a car. And if you don't think that's true, why is that true?
No, I think basically you can drive a car. I mean, think about like what drives any vehicle. It's a biological neural net with eyes, with cameras, essentially. So if and really, what is your primary sensors are two cameras on a slow gimbal, a very slow gimbal. That's your head. So if a biological neural net with two cameras on a slow gimbal can drive a semi-truck, then if you've got like 8 cameras with continuous 360-degree vision, operating at a higher frame rate and much higher reaction rate, then I think it is obvious that you should be able to drive a semi or any vehicle much better than a human.
Hi, my name is Akshay. Thank you for the event. Assuming Optimus would be used for different use cases and would evolve at different pace for these use cases, would it be possible to sort of develop and deploy different software and hardware components independently and deploy them in Optimus, so that the overall feature development is faster for Optimus?
I'm trying to see the question. Okay, all right. We did not comprehend. Unfortunately, our neural net did not comprehend the question. Yeah, so, well, next question.
Hi, I want to switch the gear to the Autopilot. So when you guys plan to roll out the FSD beta to countries other than US and Canada? And also my next question is, what's the biggest bottleneck or the technological barrier you think in the current Autopilot stack? And how you envision to solve that to make the Autopilot is considerably better than human in terms of like performance metrics like safety assurance and the human confidence? And I think you also mentioned for FSD V11, you are guys going to combine the highway and the city as a single stack and some architectural big improvement. Can you maybe expand a bit on that? Thank you.
Well, that's a whole bunch of questions. Well, we're hopeful to be able to, I think from a technical standpoint, FSD beta should be possible to roll out FSD beta worldwide by the end of this year. But for a lot of countries, we need regulatory approval, and so we are somewhat gated by the regulatory approval in other countries. But I think from a technical standpoint, it will be ready to go to a worldwide beta by the end of this year. And there's quite a big improvement that we're expecting to release next month that will be especially good at assessing the velocity of fast-moving cross-traffic and a bunch of other things. So, anyone want to elaborate?
Yeah, I guess so. There used to be a lot of differences between production autopilot and the full self-driving beta, but those differences have been getting smaller and smaller over time. I think just a few months ago, we now use the same vision-only object detection stack in both FSD and in the production autopilot on all vehicles. There's still a few differences, the primary one being the way that we predict lanes right now. So we upgraded the modeling of lanes so that it could handle these more complex geometries like I mentioned in the talk. In production autopilot, we still use a simpler lane model, but we're extending our current FSD beta models to work in all sort of highway scenarios as well.
Yeah, and the version of FSD beta that I drive actually does have the integrated stack. So it uses the FSD stack both in city streets and highway, and it works quite well for me. But we need to validate it in all kinds of weather, like heavy rain, snow, dust, and just make sure it's working better than the production stack across a wide range of environments. But we're pretty close to that. I mean, I think it's, I don't know, maybe, it'll definitely be before the end of the year, and maybe November.
Yeah, in our personal drives, the FSD stack on highway drives already way better than the production stack we have. And we do expect to also include the parking lot stack as a part of the FSD stack before the end of this year. So that will basically bring us to, you sit in the car in the parking lot and drive till the end of the parking lot at a parking spot before the end of this year.
Yeah, and in terms of the fundamental metric to optimize against is how many miles between a necessary intervention. So just massively improving how many miles the car can drive in full autonomy before an intervention is required that is safety critical. So yeah, that's the fundamental metric that we're measuring every week, and we're making radical improvements on that.
Oh, hi. Thank you. Hi. Thank you so much for the presentation. Very inspiring. My name is Daisy. I actually have a non-technical question for you. I'm curious, if you were back to your 20s, what are some of the things you wish you knew back then? What are some advice you would give to your younger self?
Well, I'm trying to figure out something useful to say. Yeah, join Tesla would be one thing. Yeah, I think just generally try to expose yourself to as many smart people as possible. I don't know, read a lot of books. I did do that though. So I think there's some merit to just also not being necessarily too intense and enjoying the moment a bit more. I would say to 20 or 20-something me, just stop and smell the roses occasionally would probably be a good idea. It's like when we were developing the Falcon 1 rocket and on the Kwajalein Atoll, and we had this beautiful little island that we were developing the rocket on, and not once during that entire time did I even have a drink on the beach. I'm like, well, I should have had a drink on the beach. That would have been fine.
Thank you very much. I think you have excited all of the robotics people with Optimus. This feels very much like 10 years ago in driving, but as driving has proved to be harder than it actually looked 10 years ago, what do we know now that we didn't 10 years ago that would make, for example, AGI on a humanoid come faster?
Well, I mean, it seems to me that AGI is advancing very quickly. Hardly a week goes by without some significant announcement. And yeah, I mean, at this point, like AI seems to be able to win at almost any rule-based game. It's able to create extremely impressive art, engage in conversations that are very sophisticated, write essays, and these just keep improving. And there's so much more, so many more talented people working on AI, and the hardware is getting better. I think AI is on a a strong exponential curve of improvement, independent of what we do at Tesla. And obviously, we'll benefit somewhat from that exponential curve of improvement with AI. Like Tesla just also happens to be very good at actuators, at motors, motors, gearboxes, controllers, power electronics, batteries, sensors, and really, like I'd say that the biggest difference between the robot on 4 wheels and the robot with arms and legs is getting the actuators right. It's an actuators and sensors problem. And obviously, how you control those actuators and sensors, but it's actuators and sensors and how you control the actuators. It's I don't know. We have to have like the ingredients necessary to create a compelling robot, and we're doing it. So.
Hi, Elon. You are actually bringing the humanity to the next level. Literally, Tesla and you are bringing the humanity to the next level. So you said Optimus Prime, Optimus will be used in next Tesla factory. My question is, will a new Tesla factory will be fully run by Optimus program? And when can general public order a humanoid?
Yeah, I think we're going to start Optimus with very simple tasks in the factory. Like maybe just like loading a part, like you saw in the video, loading a part, carrying a part from one place to another, or loading a part into one of our more conventional robot cells that welds the body together. So we'll start, just trying to, how do we make it useful at all? And then gradually expand the number of situations where it's useful. And I think that the number of situations where Optimus is useful will grow exponentially, like really, really fast. In terms of when people can order one, I don't know. I think it's not that far away. Well, I think you mean when can people receive one? So I don't know. I'd say probably within 3 years, and not more than 5 years. Within 3 to 5 years, you could probably receive an Optimus.
I feel the best way to make the progress for AGI is to involve as many smart people across the world as possible. And given the size and resource of Tesla compared to robot companies, and given the state of humanoid research at the moment, would it make sense for the kind of Tesla to sort of open source some of the simulation hardware parts? I think Tesla can still be the dominant platformer where it can be something like Android OS or like iOS stuff for the entire humanoid research. Would that be something that, rather than keeping the Optimus to just Tesla researchers or the factory itself, can you open it and let the whole world explore humanoid research?
I think we have to be careful about Optimus being potentially used in ways that are bad, because that is one of the possible things to do. So I think we'd provide Optimus where you can provide instructions to Optimus, but where those instructions are governed by some laws of robotics that you cannot overcome. So, not doing harm to others, and you would have, I think, probably quite a few safety-related things with Optimus. Yeah. So, all right, we'll just take maybe a few more questions, and then thank you all for coming.
Questions, one deep and one broad. On the deep, for Optimus, what's the current and what's the ideal controller bandwidth? And then in the broader question, there's this big advertisement for the depth and breadth of the company. What is it uniquely about Tesla that enables that?
Anyone want to tackle the bandwidth question?
Yeah. So the technical bandwidth of the...
Close to your mouth and loud.
OK. For the bandwidth question, you have to understand or figure out what is the task that you want it to do, and what is the if you took a frequency transform of that task, what is it that you want your limbs to do? And that's where you get your bandwidth from. It's not a number that you can specifically just say. You need to understand your use case. And that's where the bandwidth comes from. What was the broad question? I don't quite remember.
The breadth and depth thing. I can answer the breadth and depth, but yeah.
We can still
I mean, it's interesting. On the bandwidth question, I think we probably will just end up increasing the bandwidth, or which translates to the effective dexterity and reaction time of the robot. It's safe to say it's not 1 hertz, and it's maybe you don't need to go all the way to 100 hertz, but I don't know, maybe 10, 25, I don't know. Over time, I think the bandwidth will increase quite a bit, or translated to dexterity and latency. You'd want to minimize that over time. Yeah. Minimize latency, maximize dexterity. I mean, in terms of breadth and depth, I guess we're a pretty big company at this point, so we've got a lot of different areas of expertise that we necessarily had to develop in order to make autonomous, or in order to make electric cars, and then in order to make autonomous electric cars. We've just, I mean, Tesla is like a whole series of startups, basically, and so far they've almost all been quite successful. So we must be doing something right. And I consider one of my core responsibilities in running the company is to have an environment where great engineers can flourish. And I think in a lot of companies, I don't know, maybe most companies, if somebody's a really talented, driven engineer, they're unable to actually, their talents are suppressed at a lot of companies. And it's, and some of the companies, the engineering talent is suppressed in a way that is maybe not obviously bad, but where it's just so comfortable, and you're paid so much money, and the output you actually have to produce is so low that it's like a honey trap, So like there's a few honey trap places in Silicon Valley where they're not necessarily, don't seem like bad places for engineers, but you have to say like a good engineer went in, and what did they get out? And the output of that engineering talent seems very low, even though they seem to be enjoying themselves. That's why I call it, there's a few honey trap companies in Silicon Valley. Tesla is not a honey trap. We're demanding, and it's like, we're going to get a lot of shit done, and it's going to be really cool, and it's not going to be easy. But if you are a super talented engineer, your talents will be used, I think, to a greater degree than anywhere else. SpaceX also that way. So.
Hi, Ilan. I have 2 questions. So both to the Autopilot team. So the thing is, like, I have been following your progress for the past few years. So today you have made changes on like the lane detection. Like you said that like previously you were doing instance semantic segmentation. Now you guys have built transform models for like building the lanes. So what are some other common challenges which you guys are facing right now, like which you are solving in future as a curious engineer, so that like we as a researcher can work on those, start working on those? And the second question is like I'm really curious about the data engine. Like you guys have like told a case like where the car is stopped. So how are you finding cases which is very much similar to that from the data which you have? Like, so a little bit more on the data engine would be great. So that's it.
Okay. I'll start answer the first question using Occupancy Network as an example. So what you saw in the presentation did not exist a year ago. So we only spent 1 year amount of time. We actually shipped more than 12 Occupancy Network. And to have one foundation model actually to represent the entire physical world around everywhere and in all weather conditions is actually really, really challenging. So only over a year ago, we're kind of like driving a 2D world. If there's a wall and if there's a curve, we kind of represent with the same static edge, which is obviously not ideal, right? There's a big difference between a curb and a wall. When you drive, you make different choices, right? So after we realized that we have to go to 3D, we have to basically rethink the entire problem and think about how we address that. So this will be like one example of challenges we have conquered in the past year.
Yeah, to answer the question about how we actually source examples of the tricky stopped cars, there's a few ways to go about this, but 2 examples are: one, we can trigger for disagreements within our signals. So let's say that parked bit flickers between parked and driving, we'll trigger that back. And the second is we can leverage more of the shadow mode logic. So if the customer ignores the car, but we think we should stop for it, we'll get that data back too. So these are just different, like various trigger logic that allows us to get those data campaigns back.
Hi.
Sorry, go ahead.
Thank you for the amazing presentation. Thanks so much. So there are a lot of companies that are focusing on the AGI problem. And one of the reasons why it's such a hard problem is because the problem itself is so hard to define. Several companies have several different definitions. They focus on different things. So what is Tesla, how is Tesla defining the AGI problem? And what are you focusing on specifically?
Well, we're not actually specifically focused on AGI. I'm simply saying that AGI seems likely to be an emergent property of what we're doing. Because we're creating all these autonomous cars and autonomous humanoids that are actually with a truly gigantic data stream that's coming in and being processed. It's by far the most amount of real-world data, and data you can't get by just searching the internet, because you have to be out there in the world and interacting with people and interacting with the roads and just, Earth is a big place. And reality is messy and complicated. So I think it's sort of like it just seems likely to be an emergent property of if you've got, tens or hundreds of millions of autonomous vehicles and maybe even a comparable number of humanoids, maybe more than that on the humanoid front. Well, that's just the most amount of data. And if that video is being processed, it just seems likely that, the cars will definitely get way better than human drivers, and the humanoid robots will become increasingly indistinguishable from humans, perhaps. And so then, like I said, you have this emergent property of AGI. And arguably, humans collectively are sort of a super intelligence as well, especially as we improve the data rate between humans. I mean, the thing like that seemed to me way back in the early days of the internet was like the internet was like humanity acquiring a nervous system, where now all of a sudden any one element of humanity could know all of the knowledge of humans by connecting to the internet, almost all the knowledge, or certainly a huge part of it. Whereas previously, we would exchange information by osmosis. We'd have to, like, in order to transfer data, so you would have to write a letter. Someone would have to carry the letter by person to another person, and then a whole bunch of things in between. And then it was like, yeah, I mean, insanely slow when you think about it. And even if you were in the Library of Congress, you still didn't have access to all the world's information, and you certainly couldn't search it. And obviously, very few people are in the Library of Congress. So, I mean, one of the great sort of equality elements, like the internet has been the biggest equalizer in history in terms of access to information and knowledge. And any student of history, I think, would agree with this, because you go back 1,000 years, there were very few books, and books would be incredibly expensive, and only a few people knew how to read, and only an even smaller number of people even had a book. Now look at it, like you can access any book instantly. You can learn anything basically for free. It's pretty incredible. So, I was asked recently, what period of history would I prefer to be at the most? And my answer was right now. This is the most interesting time in history, and I read a lot of history. So let's do our best to keep that going. Yeah. And to go back to one of the earlier questions I would answer, like the thing that's happened over time with respect to Tesla Autopilot is that the neural nets have gradually absorbed more and more software. And in the limit, of course, you could simply take the videos as seen by the car and compare those to the steering inputs from the steering wheel and pedals, which are very simple inputs. In principle, you could train with nothing in between, because that's what humans are doing with a biological neural net. You could train based on video, and what trains the video is the moving of the steering wheel and the pedals, with no other software in between. We're not there yet, but it's gradually going in that direction. All right, well, maybe last question.
How you going?
I think we've got a question at the front here. Hello, there, right there. Oh, we'll do two questions, fine.
Over there or here?
Hi, thanks for such a great presentation.
We'll do your question last.
Okay, cool. With FSD being used by so many people, do you think, how do you evaluate the company's risk tolerance in terms of performance statistics? And do you think there needs to be more transparency or regulation from third parties as to what's good enough, and defining like thresholds for performance across so many miles?
Sure. Well, the number one design requirement at Tesla is safety. So, and that goes across the board. So, in terms of the mechanical safety of the car, we have the lowest probability of injury of any cars ever tested by the government for just a passive mechanical safety, essentially crash structure and airbags and whatnot. We have the highest rating for active safety as well. I think it's going to get to the point where the active safety is so ridiculously good, it's like just absurdly better than a human. And then with respect to Autopilot, we do publish this, broadly speaking, the statistics on miles driven with cars that have no autonomy, or Tesla cars with no autonomy, with kind of hardware 1, hardware 2, hardware 3, and then the ones that are in FSD beta. And we see steady improvements all along the way. And sometimes there's this dichotomy of, should you wait until the car is like, I don't know, 3 times safer than a person before deploying any technology? But I think that is actually morally wrong. At the point at which you believe that adding autonomy reduces injury and death, I think you have a moral obligation to deploy it, even though you're going to get sued and blamed by a lot of people, because the people whose lives you saved don't know that their lives are saved, and the people who do occasionally die or get injured, they definitely know, or their estate does, that it was, whatever, there was a problem with Autopilot. That's why you have to look at the numbers in sort of total miles driven how many accidents occurred, how many accidents were serious, how many fatalities. And we've got well over 3 million cars on the road, so that's a lot of miles driven every day. It's not going to be perfect, but what matters is that it is very clearly safer than not deploying it. Yeah. So I think last question. I think, yeah, so thanks. Well, the last question here.
Okay. Okay. Hi. So I do not work on hardware, so maybe the hardware team and you guys can enlighten me. Why is it required that there be symmetry in the design of Optimus? Because humans, we have handedness, right? We use some set of muscles more than others. Over time, there is wear and tear, right? So maybe you'll start to see some joint failures or some actuator failures more over time. I understand that this is extremely pre-stage. Also, we as humans have based so much fantasy and fiction over superhuman capabilities. Like all of us don't want to walk right over there. We want to extend our arms, and like we have all these, a lot of fantastical designs. So considering everything else that is going on in terms of batteries and intensity of compute, maybe you can leverage all those aspects into coming up with something, well, I don't know, more interesting in terms of the robot that you're building. And I'm hoping you're able to explore those directions.
Yeah, I mean, I think it would be cool to have, like, make Inspector Gadget real. That would be pretty sweet. So, yeah, I mean, right now we just want to make a basic humanoid work well, and our goal is fastest path to a useful humanoid robot. I think this will ground us in reality, literally, and ensure that we are doing something useful. Like, one of the hardest things to do is to be useful, to actually, and then to have high utility under the curve of, like, how many people did you help, and how much help did you provide to each person on average, and then how many people did you help? The total utility, like trying to actually ship useful product that people like to a large number of people is so insanely hard. It boggles the mind. That's why, like I said, man, there's a hell of a difference between a company that has shipped product and one that has not shipped product. This is night and day. And then even once you ship product, can you make the value of the output worth more than the cost of the input, which is, again, insanely difficult, especially with hardware. So, but I think over time, I think it would be cool to do creative things and have like 8 arms and whatever, and have different versions, and maybe, there'll be some hardware, like companies that are able to add things to an Optimus, like maybe we add a power port or something like that, or attachment. You can add attachments to your Optimus, like you can add them to your phone. There could be a lot of cool things that could be done over time, and there could be maybe an ecosystem of small companies or big companies that make add-ons for Optimus. So with that, I'd like to thank the team for their hard work. You guys are awesome, and yeah. And thank you all for coming, and for everyone online, thanks for tuning in. And I think this will be one of those great videos where you can, like, if you can fast forward to the bits that you find most interesting. But we try to give you a tremendous amount of detail, literally, so that you can look at the video at your leisure, and you can focus on the parts that you find interesting and skip the other parts. So thank you all, and we'll do this. Try to do this every year, and we might do a monthly podcast even. But I think it'd be great to sort of bring you along for the ride and like show you what cool things are happening. And yeah, thank you. All right, thanks.
Hey everyone. Well, I mean, this is definitely a new approach. We got the Tesla drive-in movie theater, basically. It's good to see everyone. It's a little hard to read the room with everyone being in cars, but it's it's the only way we could do it. So hopefully it's cool, and hopefully you can hear me. Can you guys hear me? Okay. All right, great. All right, well, thanks for coming. I think it's been an incredible year, and I'd like to thank you for your support through tough times, good times. It's been great. Really appreciate everyone who's put their hard-earned money into Tesla, and I think it's worked out pretty well. This has been a good year, and I think there's many good years to come. So I'll go through the sort of the shareholder presentation, I think, fairly quickly, because the sort of real main event here is Battery Day. So, really, I'm just going through a recap of what's happened over the past year or so. I think starting from in terms of our ability to create a factory, huge kudos to the Tesla Shanghai team for being able to go from literally a dirt pile to volume production in 15 months. It's like, damn. Yeah. So, and I think something that's really quite noteworthy here is Tesla is the only foreign manufacturer to have a 100% owned factory in China. So this is often not well understood or not appreciated, but to have the only 100% owned foreign factory in China is a really big deal, and it's paying huge dividends here. So we really wouldn't have the results that we have had this year without the great efforts of the Tesla China team. So I'm super appreciative of that. And we'll see the Shanghai factory continue to scale quite a bit from where it is right now. I think we really could expect that to be, over time, a factory that produces over 1 million vehicles a year. Yeah, it's cool. So let's see. So we also reached in the past year volume production of the Model Y, and this was the smoothest launch that we've ever had. So I think we're definitely getting better at new vehicle launches and building factories and scaling production. As you've heard me say before, it's the hardest thing is scaling production, especially of a new technology. It's insanely difficult. Making a prototype is relatively easy, and if I think of what is the real achievement of Tesla in sort of car company terms, it's like it wasn't making sort of exciting prototypes. It was that Tesla was really the first company in about a century in the U.S., the first U.S. company in the U.S. to reach volume production and be sustainably profitable. Like the crazy thing is this has really not happened in 100 years. That's the actual super hard part. And we now have 4 vehicles in volume production, S3, XY. So also the toughest joke, I think, maybe ever. It was a very difficult joke to make. So we also introduced the lowest cost solar in the US. It's only $1.49 a watt. And we really just simplified the whole value chain. So reduced sales and advertising, got rid of a bunch of unnecessary costs, and really are just relying upon the fact that it's just the lowest cost, most efficient solar in the US, providing both retrofit and the solar glass roof, which I think is a really great product, a hard product to make work, but it will be a major product line in the future. And we also got 4 consecutive quarters of GAAP profitability, which was very difficult. Yeah. So, and certainly a testament to the hard work of people at Tesla. I mean, to do this in extremely difficult times against a wide range of adverse circumstances was insanely hard. but we got it done. So, and I think the future is looking like, I think very promising from sort of an annual profitability standpoint. So, in order to achieve, in order to sort of do well financially, you really need economies of scale, and you need ideally the best technology. And I think we've had the best technology for a while, but now we are also achieving economies of scale. So, and we're also rapidly improving autonomy, which is a massive value add to each car. So, I think the value of Tesla is going to be like total, just on the vehicle side, total vehicles produced times the value of autonomy. That's a way to think about the future value of Tesla. We also have consistent free cash flow generation. This is really important for growth. And a key element here is tightening up the time from when a car is ordered to when it is built and delivered. So for a company that's growing rapidly, it's extremely important to tighten the supply chain and to have, from when parts arrive, put it into a car very quickly and deliver the car very quickly to the customer. And if you can do that inside the sort of your kind of payables timeline, then the faster you grow, the more cash you have. Or conversely, if you're unable to do it within your payables timeline, the faster you grow, the less money you will have, which is obviously bad. It's for a capital-intensive situation. So just tightening up and having the parts move very quickly to the factory, put it in a car, get it to a customer, makes a massive difference to cash flow generation. And I mean, that's why it's extremely important to have a factory in each continent. Because if you don't at least have a factory in the continent, it is impossible to achieve this. So having a factory in China that's able to serve China, and then soon many other countries in the region, will be key to us tightening that total sort of chain of cash flow and getting it, essentially, the faster we grow, the more cash. This is really important. That's also why it's important to have Giga Berlin complete, because then we'll have a factory in China, a factory in the US, and soon a second factory in the US in Austin, and a factory in Europe. And I mean, even for Giga Texas in Austin, even if we had exactly the same costs as in California, it would still be advantageous to do it there because it's roughly 2/3 of the way across the US. So in terms of delivering cars to the central US and to the East Coast, it's just faster, costs less, and it fundamentally improves our economics. So I think this is also maybe something that's not fully appreciated of just how important it is to have a factory at least on the continent or reasonably close to where the end customers is, so you can tighten that whole chain. Industry performance. While the rest of industry has gone down, Tesla has gone up. I think this speaks to, thanks. And so I'd like to thank all the customers for taking a chance on Tesla and buying our product, and really hope you're enjoying it. This is really, our sales, as Al was saying, really grow by word of mouth. So this is really, I think, a very pure, it's very pure in the sense that it's like, it's growing on the basis of existing owners recommending it to new customers. This is really, I think, a good way to grow. And then in 2019 we had 50% growth, and I think we'll do really pretty well in 2020. Probably somewhere between 30 to 40% growth, despite a lot of very difficult circumstances. I mean, there's so many, pandemic, wildfires. It's like a whole bunch of difficult production issues. But thanks to the hard work of the Tesla team and a lot of innovative approaches to overcoming issues, we're able to still see significant growth in one of the most difficult, in fact, I'd say probably the most difficult year of Tesla's existence. So, and we also published our extended impact report. At Tesla, we try very hard to do the right thing. If the right thing does not happen, it's just because we maybe made a mistake or weren't aware of it. But we always try to do the right thing as to the best of our ability. and then we published the extended impact report to show, just a sort of a self-examination of, okay, what are we doing right? What are we doing wrong? What can we do better in the future? We're definitely trying to accomplish the most good, and so, if we occasionally make a mistake, we work quickly to fix it and do the right thing. So, it's worth looking at like the average life cycle emissions in the U.S. And just how much better a Tesla is than, or an electric car, than any other, than any kind of gasoline car. And what we'll talk about in the battery day is also just how much the grids around the world and actually, especially in the U.S., are greening. It's actually much faster than I think people realize. The U.S. is moving towards sustainable energy. And so as we move more and more to sustainable energy, then effectively you end up building the solar factories and the car factories themselves with solar. Over time you do, or with sustainable energy. Over time you'll even mine with sustainable energy, and eventually it will get to an effective emissions of 0. So that's where things will end up. Yeah. So we also have safety at the core of our design. The Tesla cars are the safest cars ever designed. We have the lowest probability of injury of any cars ever tested by the U.S. government, and that's just passive safety. When you add active safety into that, it's even better. It's really, if safety is important to you, which obviously it is, the safest car you could drive is a Tesla. So, I think some people aren't aware of this, but it's really, safety is paramount. It is actually the #1 design objective when we build a Tesla is safety. Our factories are also becoming safer, and if you look at the sort of accidents per total vehicle made, it's dramatically better than in the past, and it's already better than industry average, and we're confident we can get it to the best in the auto industry. Autopilot functionality continues to improve, and you can see it in the safety report that we publish every quarter. It's just getting better and better. The U.S. average for collisions is at roughly 2.1 per million miles, and with Autopilot engaged, it's 0.3. I mean, this is a profound difference. It really massive, and this will get even better. So we're confident that over time we can get the probability of an accident, especially the probability of injury, to 10 times better than the industry average, like an order of magnitude better. So that's just a lot of lives saved and a lot of injuries avoided. So that's a huge priority for us. On the autopilot front, I think it's kind of hard for people to judge the progress of autopilot. Like I'm driving. As a matter of course, I've always done this. I drive the bleeding edge alpha build of Autopilot, and so I sort of have insight into what is going on. Previously, about a couple of years ago, we were kind of stuck in a local maximum. So we were improving, but like the improvements kind of started tailing off and just not getting where they needed to be. I call this sort of getting trapped in a local maximum. And so we had to do a fundamental rewrite of the entire Autopilot software stack, and all of the labeling software as well. So we're now labeling in 3D video. So this is hugely different from previously where we were labeling essentially a bunch of single images from the 8 cameras, and they would be labeled at different times by different people. And some of the labels, you literally can't tell what it is you're labeling. So it basically made it sort of in some cases impossible to label, and the labels had a lot of errors. Now, with our new labeling tools, we label it in video. So we actually label entire video segments, and the system, so you get basically a surround video thing to label, and with the surround video and with time. So it's now taking all cameras simultaneously, and looking at how the images change over time and labeling that, and then the sophistication of the neural nets in the car and the overall logic in the car has improved dramatically. I think we'll hopefully release a private beta of Autopilot, or the full self-driving version of Autopilot, in, I think, a month or so, and then people will really understand just the magnitude of the change. It's profound. So, yeah. Anyway, so you'll see it's just like a hell of a step change. But because we had to rewrite everything, labeling software, just the entire code base, it took us quite a while, and the sort of new I call it like 4D in the sense that it's 3 dimensions plus time. It's just taken us a while to rewrite everything, and so you'll see what it's like. It's amazing. Yeah, it's just clearly going to work. Tesla core competencies, we've got engineering, obviously, but also manufacturing. I think manufacturing is underappreciated in general, and the difficulty of designing the machine that makes the machine is vastly harder than the machine itself. So, the designing, like making a Model 3 or Model Y or Cybertruck prototype is really quite trivial compared to designing the factory that makes it. Especially if it's new technology and you want to use new manufacturing methods, it's just at least 10 to 100 times harder to do the factory than the prototype. And that's why you see a lot of companies out there or startups, they'll bring out a prototype, but they just can't get it over the hump for manufacturing, because manufacturing of new technology especially is the hardest thing by far. Like basically the prototype is at best 10% of the difficulty and probably closer to 1%. And then software. Tesla is both a hardware and a software company. So a huge percentage of our engineers are actually software engineers. And you can think of our car as kind of like a laptop on wheels. And so software is incredibly important. And so not just in the car, but also in the factory. So the factory software is extremely important. Just software in general. These are fundamental. These are the 3 critical areas that are needed to make for an awesome company. So, yeah. So we have now we'll soon have 3 new factories, incremental, on, well, we have one already, on 3 different continents. Shanghai, we're expanding to Shanghai with the 2nd phase. Berlin is making rapid progress, and Texas is making even faster progress. So, yeah. With each factory, what we're trying to do is also improve the manufacturing technology. So, it's in some cases, like the Model Y made in Berlin might look the same, but it actually is made in a much more efficient way. And yeah, we'll talk about that later in the battery presentation. Yeah, launched Megapack. It's 3 megawatt-hours all-in-one energy storage solution. So it's been great overall. Yeah. All right, and I think that's basically it. Right? All right, thank you. All right. Well, thanks everyone for coming, and we'll be back in a little bit to go through the battery stuff. And there's a little bit more, in addition to the battery stuff, we got a few extras as well. So I think you'll really like what we have to say on batteries. The battery stuff we're going to talk about is truly revolutionary and essential to Tesla's goal. The fundamental good of Tesla. It's like if you look back in history and say what good did Tesla do? The good will be to by how many years did we accelerate sustainable energy? That's like the true metric of success. It matters if sustainable energy happens faster or slower, and so that's really like how I think about Tesla and how we should sort of assess our progress. By how many years did we accelerate sustainable energy? And what we're going to talk about with batteries and a few other things will really explain how we're going to make a step change improvement in the acceleration of sustainable energy. Thank you.
Hi, folks. That was great. We're going to take a short break before we begin the Battery Day event. So stay tuned. If you're local and here in the audience today, you can feel free to get out of the cars and stretch your legs. But try to stay near the cars because we're going to begin promptly in a little bit. See you soon.
Hello, everyone. Sure. Thanks, Elon. Oh, hi. I'm Drew Baglino, SVP of Powertrain and Energy Engineering at Tesla, and I'm incredibly excited to talk about what we've been doing at batteries here at Tesla.
Great. So let's see. You got the clicker.
Yeah, I've got the clicker. Yeah.
Okay. I'll take it first, perhaps.
Sure.
So obviously the issues we're facing are very serious. With climate change, and we're experiencing these issues on a day-to-day basis. It's incredibly important we accelerate the advent of sustainable energy. Time really matters. This presentation is about accelerating the time to sustainable energy. So the past 5 years were the hottest on record. We have what looks like a wall for CO2 ppm. It's obviously, this time is not like the past. It's really important that we take action. Running this climate experiment is insane. So,
especially when it's just a transitory one anyway.
Yes.
We're going to run out of these fossil fuels. Let's just move to the future and not run this experiment any longer.
Yeah. Maybe talk a bit louder.
You got it.
Okay. So anyway, there is a lot of good news, though. A lot of people may not be aware that wind and solar comprise 75% of new electricity capacity in the U.S. this year. So this is a really major. So the grid is going sustainable very, very quickly. Now, it's also worth noting that the length of time that power plants last is on the order of 25 years. So even if 100% of energy generation was sustainable, it would still take 25 years to convert the grid. And it's also worth noting that in the past 10 years, power production from coal has dropped in half. So it went from 46% of electricity in 2010 to 23% in 2020. So this is a massive improvement. So good things are happening on a lot of levels. We just need to go faster. So in terms of Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generated. So I think solar is sometimes underweighted at Tesla, but it is a massive part of our future. The three parts of a sustainable energy future are sustainable energy generation, storage, and electric vehicles. So we intend to play a significant role in all three. So to accelerate the transition to sustainable energy, we must produce more EVs that need to be affordable and a lot more energy storage while building factories faster and with far less investment. So goal number one is a terawatt-hour scale battery production. So tera is the new giga, and a terawatt is 1,000 times more than a gigawatt. So we used to talk in terms of gigawatts. In the future, we'll be talking in terms of terawatt hours. So this is what's needed in order to transition the world to sustainability.
Yeah, and you can see we're talking about 100x growth in batteries for electric vehicles to achieve this mission. And we are going to get there. It's just a matter of how fast, and our intention is to accelerate it.
Yeah. You basically need on the order of roughly 10 terawatt hours a year of battery production to transition the global fleet of vehicles to electric.
And the average vehicle lasts 15 years, so we're talking about 150 terawatt hours, give or take, to transition the whole all vehicles of all types to electric.
Yeah, so it's a lot of batteries, basically. Yeah, so.
And then on the grid side, we have a similar mountain to climb, 1,600 times growth from today's grid batteries to go 100% renewable on the grid and to take all of the existing heating fossil fuel uses in homes and businesses 100% electric.
Yeah, and this number, I think, might grow even more, as the world economy
matures and as countries with high populations industrialize, we could see this number be even more. But let's say it's like roughly 20 to 25 terawatt hours per year, sustained for 15 to 25 years to transition the world to renewable. This is a lot.
Yeah.
So today's batteries cannot scale fast enough. They're just too small. For Giga Nevada, 150 gigawatt hours per year is like what we probably expect to make out of there. But this is really pretty small in the grand scheme of things. That's only 0.15 terawatt hours. And they cost too much. So
we would need 135 fully built out Nevada gigafactories to achieve 20 terawatt hours a year. It's not scalable enough of a solution. We need a dramatic rethink of the cell manufacturing system to scale as fast as we can and should.
yeah, and I think we should view this as more than just a question of money. Money is sort of like an ethereal thing, but it's really the amount of effort. You have a certain amount of effort, in terms of people and machines, and depending on how efficient that effort is, for a given amount of effort, you want the most amount of batteries. So it's not just a question of like, well, if we had $2 trillion, tomorrow you could make this. It's not that easy. You actually need to organize a massive number of people, build a lot of machines, build the machines that make the machines. And so it's incredibly important to have that effort yield the most number of batteries. So, and then goal two, obviously, we need to make more affordable cars. I think one of the things that troubles me the most is that we don't yet have a truly affordable car, and that is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down. We've got to make, and we've got to be better at manufacturing, and we need to do something about this curve. The curve of the cost per kilowatt hour of batteries is not improving fast enough. So we've given this a lot of thought over many years to say, okay, how can we radically improve the cost per kilowatt hour curve? It's been somewhat flattening out, actually, in recent years. So
I mean, early growth was promising, but you can see we're kind of plateauing. So that's what's motivating us to rethink how cells are produced and designed.
Yeah, exactly. Yeah, and EV market share is growing, but EVs, aren't still accessible to all. And you can see, as Drew was saying, it's like starting to flatten out a little bit because the rate of improvement of the affordability of cars is just not fast enough. So that's why we got Battery Day.
Yeah. To make the best cars in the world, we design vehicles and factories from the ground up. Next.
Yeah.
And now we do this for batteries as well.
Yeah. It's weird, the slides don't show up quite right. Anyway, what shows up on the screen is not quite what shows up there. Anyway.
Oh, okay.
It's different.
Yeah, I think it's because that's,
No, that one's current, supposed to be current. Anyway.
So let's get started. We have a plan to halve the cost per kilowatt hour.
Yeah.
And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. And we're going to go through that plan with you today, step by step, and build up how we get to these goals and how we accelerate this transition and make our vehicles and our grid batteries more affordable.
Yeah, I mean, we basically thought through every element of the battery, well, almost every element. There are a few more elements that we won't get to today, but we will get to in the future.
Yes. So first, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. So it's quite a long winding process. And you can see the tab still there. And then To explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we, there we go, discharge the cell. Got lithium moving from anode to cathode, and then the reverse. When we charge the cell, anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, whether they're no matter what the form factor is. And when we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future.
Actually, so a slight note on why is the one called the 18650, although not on the slide, versus the 2170, is that the first two digits refer to the diameter, and the second two digits refer to the length. So that helps explain why are these weird. What's up with these weird numbers? But like nobody could explain to me why there was an extra zero. So I said, like, okay, well, we're deleting the zero that nobody can explain in future form factors. So that's why it's technically it's like the 18650 bizarrely, but going forward it's the 2170 because we just got rid of the extra zero because it's pointless.
And this was a evolutionary step, going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at us in front of us, and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like anybody could make a bigger form factor.
Any fool could make a bigger form factor. We not any fool.
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
That's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is, again, like this is quite hard to do. So it's nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a freaking tabless cell and have it actually work and then connect that to the top cap. And it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything. But
sometimes what's elegant and simple is still hard, and it took us a lot of trials, but we're happy where we ended up.
Yeah, I mean everything's simple in recollection. After you simple, everything it's hard until it's discovered, and then it's simple. So anyway, but there's a lot of really cool things going on that enable tabless, and it's really due to a really great engineering team. Drew and the rest of the team have done amazing work in achieving this tabless construction. And it sounds, I think it may sort of sound a bit silly to some people, but this is like, for people that really know cells, this is a massive breakthrough.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating.
Yeah.
And has an awesome thermal and performance benefit.
Yeah, that's just to elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then sometimes you get the tabs wrong. And you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
Yeah, so when these... yeah, it's pretty great. And just to clarify, when we see these plus 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So this is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry, where from humble beginnings, over a century of innovation has enabled mass scale, continuous motion, unbelievably low manufacturing cost. And when we think about the lithium-ion industry, which is really only in its 3rd decade of high-volume production, it has so far to go to achieve similar scale and simplicity. And that was the inspiration that we set out to the team as we thought about how to marry cell design and manufacturing in the best possible factory. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time, and where the sort of the electrochemistry is set and the quality of the cell is verified. And we set out at every step of this process to try to take that inspiration we just showed and think about how we make those processes fundamentally better and more scalable. And one of the most important processes is where it all begins, the wet process of the electrode coating. And just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven where the slurry is coated onto the foil, huge ovens, tens of meters long, dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. This is serious iron involved in making batteries. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat? And that's what the dry process really is about. And in the most basic form, you can see it here on a bench top. Literally, powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, you know, if this was easy, everyone would do it. So it's not like dry coating electrode is actually easy. It's actually very hard to do what appears to be a simple thing. And it's worth noting, like, you know, we did acquire Maxwell as like a little over a year ago, I guess. And you know, it's certainly a good company and everything, but the dry coating they had was like like sort of I would call proof of concept. Since the acquisition, we've actually revved the machine that does the dry coating 4 times. So we're in revision 4 post acquisition of the machine, and there's still a lot of work to do. So I would not say this is like completely in the bag. There's still a lot of work to do, and you know, as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you know, you make something work on your bench and bingo, now you can make a bazillion of it.
Absolutely.
It's insanely difficult to scale up.
Yeah, but if you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be clear, I would like to not say that right now it's just totally working. It's close to working, but it's not, even now at the pilot plant level, it is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah.
So
we're still ironing out the kinks, but we made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yep.
So, but this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production. The rate at which the machines are being improved is extremely rapid. Like literally every 3 or 4 months is a new rev.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
I want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, 1 line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having 1 line be 7x the capability is just effort multiplying.
Yeah. So. Yeah, you can sort of think about like the sort of the fundamental physics of a factory or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation you've got your exhaust velocity and then the log of the start to end masses. So it's basically saying, you know, how fast are things going and
what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. So
only the value-added steps.
yeah, if you break the factory down into cubic meter sections, and say, or smaller, it could be like 1 liter sections, and say, is a majority of this volume doing useful work? You would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. So I think it is possible to get to at least 10 times that volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory? It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to 2 factories basically, and the company that will be successful is the company that with 1 factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we with 1 factory achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Highbar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be 1 machine and remove all of these unnecessary steps.
Yeah, I mean, basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible. But I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to solve. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
So.
You want to take this one?
Sure. So essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. So we're able to, from a volume standpoint, actually get what, in a smaller form factor than Giga Nevada, we were able to get many times the cell output. So you can see, like, basically, we can get a terawatt hour in less space than it took to make a gigawatt hour, 150 gigawatt hours. So this is pretty profound. It's like, I would actually not have thought this was possible several years ago, that we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours. So
yes, simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission. And as Elon said, we're going to try to even improve on this as we push towards our goals, which are.
Yeah. So this is just for. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL, and so this is 100 gigawatt hours supplemental to what we buy from suppliers.
And yeah, essentially, this does like reduce our weighted average cost of a cell because but it allows us to make a lot more cars and a lot more stationary storage. And then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we can. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
When you look at the size of that factory on the previous page, it really shows how enabling all of these advancements are in achieving a 3 terawatt hour goal by 2030. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
But wait, there's more.
Yeah.
So we have a manufacturing system. We've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically, with silicon, the cookie crumbles and gets gooey. That's basically what happens.
Good analogy.
Yeah.
And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials in the scheme of things. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. And you can see some of the things that maybe you've heard of, SiO, silicon with carbon, or silicon nanowires. I mean, that's kind of the space right now. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
Yeah, and I'm not sure if you saw this. Basically, $1 per kilowatt hours.
Yeah.
Basically, if you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour.
Yeah.
And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion-conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. Cobalt is a...
Yeah, sorry, I was just going to say, it's tough to exactly figure out what the right analogy is to explain cathode and anode, but a bookshelf is probably a pretty good one, in the sense that you need a stable structure to contain the ions. So you want a structure that does not crumble or get gooey, or basically that holds its shape in both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. So if it doesn't retain its structure, then you lose cycle life, and your battery capacity drops very quickly.
Absolutely. Yeah, I totally agree. And I think people are always talking about like, oh, what's the cathode going to be? Is it NCA or whatever? You know, the thing to consider is just fundamentally what the nickel, the metals are capable of, and that's what we have on the chart here. $1 per kilowatt hour cathode of just the metal, using just LME, you know, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the energy in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode $1 per kilowatt hour.
Yeah. Big deal.
But it's not just about nickel. You want to?
Yeah, sure. So in order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. But there's also, I think we need to have a kind of a 3-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long range applications like Cybertruck and the semi. Because something like a semi truck, it's extremely important to have high energy density in order to get long range. So, just to give sort of iron a bit more time, like although if you look at the watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you've fully considered at the pack level, everything else taken into account, nickel is about maybe 50 or 60% better than iron. So iron is a little better than it would seem when you look at it at the pack level fully considered. It's not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. And so, good for stationary storage and for medium range applications where energy density is not paramount. And then, like I said, for intermediate, it's kind of a nickel manganese. And it's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off. I mean,
Yeah.
Just enough to have you still want to use 100% nickel for something like a semi-truck, but really not much of a sacrifice at all.
Yeah.
And, beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode $1 per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. Here's a view of the traditional cathode process. Effectively, if you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that's just happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproducts.
Yeah, it's insanely complicated. If you look at the total, like if you're just like, it's a small world journey of I am a nickel atom. What happens to me? And it's crazy. Like you're going around the world 3 times. There's like the moral equivalent of like digging the ditch, filling the ditch, and digging the ditch again. It's total madness, basically. And these things just grew up as they're just kind of like legacy things that it's like how it was done before. And then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution.
Yeah.
And then when you think about the fact that now we're actually just directly consuming the raw metal nickel powder, it dramatically simplifies the metal refining part of the whole process. So we can eliminate billions in battery-grade nickel intermediate production. It's not needed at all.
Yeah.
And we can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean, to be clear, cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
And on that note, the way the lithium ends up in the cell is through the cathode. So then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
Yeah. So it's important to note that there is a massive amount of lithium on Earth. So lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Like all the cars in the United States, there's like 300 million or something like that. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States.
Discovered today.
What we already know is exists.
People really haven't even been looking.
Yeah, people haven't been trying because it's just like widely available. So, but it is important to say, like, okay, what is the smartest way to take the ore and extract the lithium and do so in an environmentally friendly way? And we actually discovered again, looking at a sort of first principles physics standpoint, instead of just the way it's always been done, is we found that we can actually use table salt, sodium chloride, to basically extract the lithium from the ore. This is, nobody's done this before, to the best of our knowledge. Nobody's done this, and it's a sort of, all the elements are reusable. It's a very sustainable way of obtaining lithium, and we actually we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before, and it will not look like terrible, and yeah, it'll be nice. Nice.
Yeah.
So
simply mix clay with salt, put it in water, salt comes out with the lithium, done. I mean,
it's pretty crazy.
Yeah. So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet.
Yeah, that's true. Actually, just what's in Nevada. That's basically there's so much damn lithium on Earth. It's crazy. It's one of the most common elements on the planet.
And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why.
Yeah.
The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since we know our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
Yeah, and just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But eventually, it is the way that all resources will be made available, and that's why we're investing in this recycling facility in Nevada.
Yeah. Long-term, new batteries will come from old batteries once the fleet reaches steady state.
Right. Okay, so we just talked about scaling cathode and recycling. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
So there's an architecture that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made. And it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's a great achievement of our materials team. In fact, in general, we've got a lot of advanced materials coming for Tesla, that new alloys and materials that have never existed before. So so you're basically making the front and rear of the car as a single piece, and then that then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were like basically worse than cargo. You had to kind of bolt them down. It was very difficult. And then somebody said, "Hey, what if we just make the wing tanks? What if we just make the fuel tank in wing shape?" So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. What we do is essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat, and you have carbon fiber face sheets and, say, aluminum honeycomb between them, this gives you incredible stiffness. And it's really the way that any super fast thing works is you create basically a honeycomb sandwich with two face sheets. This is actually even better than what aircraft do, because aircraft do not do this. They can't do this because fuel is liquid. So in our case, the batteries are solid. So we can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car.
Yeah.
In fact, if this was like a convertible that had no upper structure, it would be stiffer than that convertible would be stiffer than a regular car. So this is it's just really it's really major. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of have to, you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to use to move the cells closer to the center of the car, because we don't have the in the top one we've got that sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that you can think of like when there's ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't want to know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. So, I mean, I really think that long term, in any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal. It's casting machines. It's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Yeah, so it's major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah. Yeah.
All right, so stacking it up, we're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. And yeah, so I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah, just happened to happen out that way. Yeah.
I mean, 0.420%, of course. Yeah, so what this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So, you know, it's not like if we could do this instantly, we would. But it's really, I think what this bodes for, it just really bodes well for the future, and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. So, you know, what tends to happen as companies get bigger is things tend to slow down. Well, actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
Yeah. I mean, long term, we want to try to replace about, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter where you are in the value chain, there is a ton to do. You need to rethink from first principles how you do it so that you can scale to meet all of our objectives.
Yep.
And Elon?
Sure.
What does this mean?
What does it mean for what does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it because our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a, I don't know, mass market premium, but like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah. So we have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that? Yeah. Woo. So, anyway, we took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. So we're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise. And you can order it now, and it's available basically end of next year. So, and now we'll move to Q&A.
Absolutely.
So we'll invite a few people on stage.
Come on up, team.
This is just a small portion of the team, but it would be great to show you some more of the team, and when we do Q&A, we can give various people different questions to answer.
Sounds great. Actually, I don't know how we're getting the questions.
Actually, I don't know either. Is somebody going to read them to us? Okay, well, you could just you can maybe get out of the car for 2 seconds and yell it at us. I don't know. Hey, how do we get the questions?
Oh, they're mics. Okay, wait for the mic.
Oh, there are mics. Okay, great.
All right.
Okay, we'll definitely need to give people mics because otherwise there's no way. Sorry? Okay. All right, we're going to pass some mics out. We don't have a name for the $25,000 car yet.
It's a great question, though.
Yes, we will be manufacturing cells in Berlin. Yep.
Thermal management system? For homes.
Oh, you mean like the home HVAC? Yeah, I mean, that's a pet project that I'd love to get going on. I don't know, maybe we'll start working on that next year. Because I just think man, you could really make a way better home HVAC system that's really quiet and super efficient and yeah, super energy efficient, and also has like a way better filter for particles, and yeah, and it works very reliably. And we've already developed that for the car. Like, so the heat pump in the Model Y is really pretty spectacular. I mean, it's tiny, it's efficient, it has to last for 15 years. It's got to work in all kinds of conditions, from the coldest winter to the hottest summer. So we've actually already done a massive amount of the work necessary for a really kick-ass home HVAC. And they could also like stack them. So if you want to say, depending upon the size of your house or whatever, how much you need, you can just basically stack them, and just have a very compelling, super efficient home HVAC. And then you can also communicate with the car, and it'll know when you're coming home. So it's like, oh, I don't need to keep the house cold all day. I just cool it down because I knew you were coming home. So the pack can communicate with the car and just like really dial it into when you actually need cooling and heating. It'd be great.
Fun product.
Yeah.
Who's next?
Hello. Hey guys, Eli here from Tesla Owners Club, My Tesla Adventure. Just quick question. So I'm a huge fan of car camping in my Tesla with my dream case, like my all-time favorite activity. Is it going to be possible to get climate control to the back of the Cybertruck? Because that would be the ultimate camping machine if we can get all-night climate control.
We'll try to do that. Yeah. I agree. That would be really cool. Yeah.
All right, who's next?
Hello. Long-time fan, Elon. Great guy. Just a question. How does the ICE industry look like in the future?
Well, I don't think there will be an ICE industry long term. So yeah. I mean, well, I guess there might be like a few things that are like, it's a like curious thing. Like, I mean, there's still like some steam engines made somewhere, but like they're just basically sort of quirky collector's items. I mean, that will be the future of the internal combustion engine car.
Hi, Elon. To your left here in the white Model Y. Ryan McCaffrey from the Ride the Lightning Tesla podcast. Curious about Cybertruck. It was interesting to see where you had it in on the battery technology front. I'm sort of curious what you see for it in the production front. Is its volume, trucks are so popular in America, do you see its volume equaling the 3 or the Y in the future? And also, is were you able to get Tesla is able to legally be sold in Texas as part of the Giga Texas deal?
Well, it's hard to say what the volume exactly would be for the Cybertruck. The orders are gigantic. So we have like, I don't know, well over 500,000 orders. I think maybe 600,000 or 600,000. That's a lot, basically. We stopped counting. So I think there's probably room for, I don't know, at least like a unit volume of like 250 to 300,000 a year, maybe more. Now we are designing the Cybertruck to meet the American spec, because if you try to design a car to meet the global, the superset of all global requirements, it basically, you can't make the Cybertruck. It's impossible. It really is designed for the American market, but this is the biggest market. Our North American market is the biggest market for pickup trucks by far, or large pickup trucks. And then I think for we'll probably make an international version of the Cybertruck that'll be kind of smaller, kind of like a tight Wolverine package. It'll still be cooler, but it'll be smaller because you just can't make a giant truck like that for most markets. So yeah, but it's gonna be great. And I don't know. I think probably we'll be able to sell directly in Texas. We do pretty well right now, but it is a bit weird not being able to actually conclude a transaction in Texas. But it's got to be like a click on a server based in California. So, but weirdly we can do leasing in Texas, but not selling. But hopefully that'll get cleared up in the future.
Yeah, Elon, great job with everything that you're doing. Thras Gerber from Gerber Kawasaki, your team's amazing. What I'm most curious about, these innovations are incredible, but on my drive up here, fully on autopilot for 400 miles, the entire state is brown, and this is ultimately about climate. Has there been some analysis done if all these things are achieved? What will its direct impact be on climate?
Well, I mean, I think it will have a very significant impact because it will stop the CO2 ppm from growing as it is every year. And I mean, I should say, like, I try to view the whole climate thing for as a science question as much as possible. Science, you always question your hypothesis: is it true? Is it not true? Or assign a probability to a given hypothesis. And I should say that my original interest in electric vehicles predates the climate issue. Like just when I was in high school, I thought, man, if we don't figure out electric cars, the whole economy is going to collapse when we run out of oil. So it's like, we better figure out electric cars and sustainable energy, or civilization is going to crumble. And then it was only kind of later that the significance of the climate risk became apparent. We were also able, using fracking and other types of technology, to access a lot more fossil fuels than previously thought, which is, helpful for lowering the cost of gasoline, but it's pretty bad for the total tonnage of CO2 that you could put in the atmosphere. It's now greatly beyond what people previously thought. So, but this is, as we were just going through in this presentation, it's like it is a absolutely monumental task to accelerate the advent of sustainable energy. I mean, the entire global economy is still, more than 99% dependent on, or roughly 99% dependent on fossil fuels. So although electric cars kind of get a lot of press right now, they're still, and there's still very few, as a percentage of the total global fleet, is practically nothing. I would say, yes, less than 1% of the global fleet is electric right now. Because of 2 billion cars and trucks and whatnot in use. So there's a massive amount of work ahead, just insane, like hard to comprehend how much work is ahead to get the new vehicle production to be sustainable, to massively increase the amount of stationary storage, which is critical because renewable energy is intermittent. Wind and solar is intermittent. Sometimes the wind doesn't blow, and obviously the sun doesn't shine at night. So you got to have batteries, a massive number of batteries. So
it's hard to measure in direct impact, but it's an experiment that we shouldn't be performing, and the sooner we can sort of end the experiment, the sooner we can kind of move on in a fully sustainable way that is actually lower cost. I mean, I think the thing that people haven't fully internalized is once we do get to the 25K car, the ownership cost of that car is incredibly lower than the prior car. And then on the solar side and wind, with the cost of solar and wind coming down and with batteries coming down with them, the actual cost of energy on the grid is going down. So we're sort of moving towards a sustainable, lower cost future. So there's not really a sacrifice.
Yeah, that's true. It is a false dichotomy to say that it's either prosperity or sustainability. This is often used by oil and gas to say like, oh, well, do you want people to lose their jobs? Do you want lower people's standards of living? Do you want to, make all these economic sacrifices, really, in order to have sustainability? And the reality, as Drew was saying, is that a sustainable energy is going to be lower cost, not higher cost, than fossil fuels.
Elon, quick question for you, right here in front. First, thanks for having everyone, and as telling a friend, the one company to go work for that's going to have the biggest structural impact over the next 10 years at scale, it's probably Tesla. So kudos to everyone at Tesla for what they've done to this point and going forward. The two questions for you, as you've looked at the auto and the storage markets, I know you've talked about it at kind of 50-50 long term, but it seems like a lot of the battery cost curve achievements that you've presented today really make some of these storage opportunities much more feasible over the next 5 years. And so I guess the first part of the question is, does your calculus upon learning and improving these things change on that 50-50 mix, or is there a role where storage becomes bigger? And then the second part of the question, with all these huge grand visions, who's going to be with Tesla from a corporate perspective accomplishing these things? Obviously, Tesla can't do it alone, but when you look at some of the traditional auto industry or power, et cetera, I don't see a lot of other Teslas.
Well, actually, so there's a lot of companies in China that I think are doing great work with electric vehicles and also with stationary storage. Although we don't see that much in the US yet, but I think probably we will in the future. I don't know. I mean, obviously, we're doing everything we can to encourage other companies to move to sustainable transport and also, make stationary storage batteries. We opened up, made our patents freely available. We really try to tell these companies, hey, you really need to do this or you won't exist in the future. But they don't believe it, So, I mean, we've talked until we're blue in the face. What are we supposed to do? But we really are hopeful that other companies will also do what we're doing, and that will make a sustainable future come sooner.
From a fundamental market size perspective, like we did the first ground up work to show the size of the market in terawatt hours, and they are roughly 50-50. 10 terawatt hours for transportation, 10 terawatt hours for the grid. And part of that is because the grid batteries, because when you're making a power plant, you're making a large investment, are 25-year assets or greater. If the grid batteries were 10-year kind of things, the grid market would be bigger, but because it's a longer duration asset, they're roughly the same size.
Thinking long term, is there any other segments that this new battery will be able to disrupt or electrify beyond just the initial Model 2 or cheaper sedan, like a boat, boring company, Luke, plane?
Where are you, Golly?
Are you
there?
What's up? Right here.
Okay, great.
It's
like ventriloquism here. It's like we just get the sound out of the speaker and you can't tell where the heck it's coming from.
Yeah, any hints, or is the Model 2 such a big deal because it decreases the cost of transportation that is really the disruption? Or should we get hyped that this new cost curve opens up different vehicle categories like a high passenger density bus, boring loop, boat, plane?
I mean, there are batteries in limited production right now that do exceed 400 watt-hours per kilogram, which I think is about the number you need for decent range, medium range aircraft. I think our batteries will, over time, start to approach the 400 watt-hours per kilogram range as well. Yeah, I mean, I think over time we'll see all modes of transport, with the ironic exception of rockets, transition to sustainability, or to electric, basically. On the rocket front, what we're planning to do is about 80% of Starship is liquid oxygen, and we're actually already running a power line to be able to use wind power to create the liquid oxygen. So we're making some decent progress on sustainability on the rocket front, but there's just no way to have an electric rocket, and it's important for the future of life and consciousness that we become a multi-planet species. So got to keep doing that.
Hi, Elon.
Hello.
Josh Phillips here, retail investor. I have a question in regards to the lithium and nickel industries and the likely price spikes and shortages of high-grade materials the EV industry is likely to see if they don't act fast to address future supply. Tesla have clearly made the right moves that are necessary, but there's a real worry that the potential supply issues and price spikes will create a drag on the rest of the EV industry and therefore a drag on global EV adoption. What advice would you give to the EV and mining industries to quickly solve this looming hurdles? Because for a sustainable energy future, the spice must flow. Thank you.
Yeah, indeed. The spice must flow. The new spice. I don't know. I think I'm not sure. I guess we can try to like basically overdo it in cell production and perhaps supply cells to others. But we do see the fundamental constraint as total cell production. That's why we're putting so much effort into making cells and kind of reinventing, trying to reinvent every aspect of cell production from mining the ore to a complete battery pack, because it's the fundamental constraint. We're not getting into the cell business because we, just for the hell of it. It's because it's the fundamental constraint. It's the thing that is the limiting factor for rapid growth. But we could certainly try to overdo it on cell production and perhaps sell cells to others. Although we are going at absolute top speed, so it's like it's not like we're holding it back. But I think like just making really efficient cars and that have low drag coefficient, low rolling resistance, efficient powertrains. I mean that's kind of what we've done in order to make iron phosphate still have a good range. So the iron phosphate's lower energy density solution, but there's while there are some limitations on the total amount of nickel produced every year, there's really no limit on the iron. There's so much iron, it's ridiculous. So you can really scale up iron phosphate, at a raw materials basis faster, more than you can nickel. But yeah.
And just to point out, when we were walking through this presentation, we intentionally separated all the different aspects. The benefits of structural battery apply to a iron-based cathode in the same way they apply to a nickel-based cathode. Yeah. So you get longer range iron-based vehicles, and also the silicon benefit can apply to the iron-based vehicles as well. So we can do a lot to extend the range of an iron-based vehicle, which is why it's a key part of the roadmap going forward. And then I invited Turner up here to talk about what the mining industry can do.
Yeah. Diversification on the cathode side is obviously massive, and EVs are all about efficiency. And so for the EV industry, for the vehicle industry, we need to see powertrain efficiency really increase at all other companies matching Tesla powertrain efficiency so that everyone can have that diversified cathode approach where LFP is used in medium range and even really make a 300-mile vehicle with LFP. And really the goal that we were trying to present here was a model for vertical integration, strategic vertical integration that a lot of different people can do. What we need to see is vertical integration that shortens the process path from mine to cathode. And what we're doing here is novel, and we're trying to push the industry in that direction. So we're presenting a model here that anyone can follow.
Yeah, in fact, if there's anything that you guys want to comment on, feel free to step forward and say something.
I think the key is to be smart about your chemistry choices, your materials choices.
Talk louder.
Yeah, if you're smart about your materials choices, the spice will continue to flow. Yeah. You don't need to use the same kind everywhere, and it's about strategically planning it out. And for miners, I think we are incentivizing them quite a bit to ramp up their production.
Yeah, and actually we had good calls. Like they're all motivated. I think that they've been sort of sitting back, being like, "Are you going to grow like crazy?" And we're like, "Yeah, we're going to grow like crazy." And then I think this indicates we're going to grow like crazy, and that's what the miners want to hear. And then they'll go make the investments.
Hello, Elon. This is Ben Limpick. I'm a musician. I was wondering, does Tesla have any future plans to make partnerships with music companies like it has done with 10-cent games or things like that for you guys to actually kind of expand your services for artists and other types of creative people to get involved in producing content that can be part of the Tesla ecosystem, or so other people that do creative things can get involved with you guys?
Well, we haven't really thought about that much, but I suppose it's probably something we should think about. We will be providing a title on Teslas. So we're providing more music sources that people can choose from, and just generally trying to improve the entertainment experience in the cars. And I think actually as we go to a more autonomous future, the importance of entertainment and productivity will become greater and greater. I mean, to the degree that if you're just basically sitting in your car, the car is fully autonomous and driving somewhere. It's sort of like being in a, the car is essentially your chauffeur, and then the things that become important are, okay, well, let's have good entertainment, and if you want to do some productivity stuff, then that actually starts to become much more important because you're no longer spending your attention driving the car. So it will be extremely important in the future.
Should we do some of the say.com questions? Yeah. Okay. Should we do the second one?
Yeah. The first one I think we already answered. Like if we're able to make enough cells, which we'll try to do, or we will supply other companies. It's definitely not an intentional effort to keep the cells to ourselves. If we can make enough for other companies, we will supply them. And we're trying to do the right thing for advancing the sustainable energy, whatever that is. So vehicle to grid, we get asked that a lot. I think one of the things that's important to note is the vehicle to grid. It doesn't, unless you have a power cutoff. Like you need to cut off your main supply to the grid. Otherwise, if you lose the power in your house, you'll basically just backflow energy to the grid. So just having a reversal in the power flow does not actually keep the lights on. You need a whole separate system to cut off power to the grid. And I think there's also the case that people really want the freedom to be able to drive and to charge at their house. And it's obviously really problematic if you get to morning and your car, instead of being charged, it discharged into the house, and then you're sort of, okay, now I can either drive or use the battery to power my house. I think it's actually going to be better for people's freedom of action to have a power wall and a car separate, and then it's everything works. And you add that, you basically combine that with solar, either solar retrofit or solar glass roof, and local battery storage. So you basically become your own utility, and then the car is can be charged also with solar. I think that's like the stuff that works. That said, like we can certainly do vehicle to grid. I think we can basically enable that with software in Europe or something, right?
Yeah. We are future generations of power electronics. We will be able to do this more or less everywhere from a energy market participation perspective. But yeah, from a backing up the house, and it just so happens that the way the North American connectors are on all the cars in North America, it doesn't matter whether it's the Tesla connector or the connector that the other vehicles have, doesn't actually support powering your home. It's unfortunate. So you'd need an additional hardware to do that. But yeah, in the future, all versions of our vehicles will be able to at least do bidirectional power flow for the purposes of energy market participation. But even for that, it's important to remember that your car isn't plugged in 24/7. So it's kind of an unpredictable resource for the grid. It'll have a value, but it's not the same as a stationary battery pack.
Yeah, honestly, a vehicle to grid sounds good, but I think actually has a much lower utility than people think. I think very few people would actually use vehicle to grid, and we actually had with the original Roadster, we had vehicle to grid capabilities. Nobody used it.
Yep. How do we find the engineers to do everything we're saying?
How do we find the engineers to do all these things? I guess we recruit a lot of engineers from all parts of the world. I think Tesla has a good reputation for doing exciting engineering, and that tends to attract a lot of the top engineers in the world, because they know that their efforts at Tesla will really serve the greater good, and we're super hardcore about engineering. Tesla is first and foremost an engineering company. It's hardcore engineering is what we do. The sheer amount of hardcore engineering done at Tesla is insane. And if you look at, say, there's various surveys done of engineering schools, where do you want to go? What's your top choices? And actually the top two choices last few years have been Tesla and SpaceX. So sometimes it's Tesla first, sometimes SpaceX first, but those are the two top ones.
Yeah, I mean, if you are motivated to solve some of these problems, which are the hardest problems in the world to solve, that really fundamentally enable the future we all need, please reach out.
Yeah, and
help us work on these problems.
Absolutely, and like we said, the battle is far from over. Less than 1% of the global automotive fleet has been converted to electric, and even maybe less than 0.1% of stationary storage has been done. So stationary storage has barely begun. Converting the global vehicle fleet to electric has barely begun. So there's still a massive amount of engineering work to be done at Tesla and other companies to accelerate this transition to sustainability.
Hey, can you guys hear me?
Yeah.
This is Jordan from Mark Asset Management. So you've talked about the importance of the factory, and you've mentioned the ground-up design process and a lot of the new things that you're going to be doing or started to do in Shanghai, Berlin, and Austin. Can you just maybe help us understand and quantify like how financially meaningful all of those improvements will be? And then given what you're trying to accomplish as a company, is it fair to assume that the vast majority of improvement will be given back to the customer in the form of lower prices?
Yeah, I mean, I think certainly we will try to give back as much as possible to the customers. It's not like, it's not like Tesla's profitability is crazy high. Our average profitability for the last 4 quarters is like maybe 1%. So just to be clear, it's not like, we're minting money. Our valuation makes it seem like we are, but we're not. We do want to try to make the price as competitive as we can without like losing money. And if you lose money, then if you keep losing money, you'll just die. So we have to. This thing called profit is just like we need to bring in more money than we spend, otherwise we're dead.
But affordability is key to how we scale,
Yeah.
right? Like the demand goes nonlinear as you reduce the price of the car.
Yeah, it's important to sort of separate the difference between affordability and value for money, or desirability of the product. So, for a lot of people, they want to buy a Tesla, they simply don't have enough money. We could make the car infinitely desirable, but if somebody does not have enough money, they can't buy it. Sometimes, people, kind of forget this. It's like, people have to have enough money to buy the car, and just making a car super desirable but expensive does not mean they can afford it. So it's absolutely critical that we make cars that people can actually afford. Yeah. So maybe we should
over
go
here
some of
now.
these things. Just scroll down or something. Oh.
When do you expect Tesla vehicles to beat ICE vehicles on initial purchase price? I think a way to answer that question is, in the classes of vehicles we sell today, we're already doing that.
Yeah, we're already pretty close. And then factoring in total cost of ownership, and the fact that electric vehicles require much less servicing, and are way cheaper to run. When you look at like total cost of ownership, and you can obviously lease a car. So if you just like lease a car or get a loan for a car, you've got your sort of monthly payment, and then your cost for either gasoline or electricity, and your cost of servicing. And the fully considered cost of an electric car is much less than a gasoline car of the same nominal purchase price. I mean, that said, and like maybe on the order of 3 years, when we can do a lower cost car, like a $25,000 car, I think that will be basically on par, maybe slightly better than a comparable gasoline car. So I think maybe it's on the order of 3 years-ish.
How have the technology advancements and increased vertical integration of battery manufacturing influenced your ability to improve the environmental and social impact of the supply chain? And I think, yeah.
I think we sort of have said that already.
Yeah.
Do you have some ability to scroll through this? Just scroll away.
We covered recycling.
Yeah. Well, just scroll until we've got stuff that we haven't covered.
Well, we definitely covered that top
yeah,
one.
a lot of the things we've already answered, I think.
Covered that. That one. I think
we literally just answered that.
Yeah. Oh, I saw a cathode durability question. Let's go to that one. Go down, go down, go down. Good technical question. Keep going. How are you going to address the cathode durability and cost and environmental impact trifecta? Is this something you're going to leave the upstream supply chain to solve? No, I think we tried to answer that directly. I mean, we really are looking at not just what happens in the cathode facility, but like currently outside the cathode facility that should really be inside, and removing processes that shouldn't have been there in the first place, and the use of reagents that are just costly and not necessary, and removing a bunch of wastewater from the process.
Guys, is there anything you want to add to? Maybe we could like go through everyone and like maybe say what you're doing and say a few words. I don't know.
Sure. I just want to reiterate the fact that this is a massive problem.
Massive problem.
And it seems like Tesla's on its way and ahead, but we need everybody's help because it's everybody's planet, and we're not going to get to 20 terawatt-hours by ourselves. So please think about this carefully as it affects everybody. So let's get on it.
Yeah. And obviously, if you care about solving sustainability and doing hardcore engineering, definitely come work at Tesla.
Yeah, we went through a couple of the manufacturing improvements, and it kind of looks easy when you put together a nice slide deck, but the challenges are like this. It's super challenging when you take materials out of the process, when you integrate processes together. You have to do a lot of things at once, and that's like this immense engineering challenge. And so, like, to appreciate that, like, you need, like, to get through this, we need, like, the best engineers we've got. And we've got this awesome team. I just want to shout out also to all of our team watching, like, you guys are awesome. Like, you absolutely kicked ass putting this together. And, yeah.
Yes. Thank you.
Thank you, Tesla team. Totally agree.
Yeah, that's it. Like, yeah.
Okay. Yeah. Rodney Westmoreland, managing the construction here at Tesla. What I would like to say is, one, shout out to the team. The team has been working effortlessly. A very, very tough project here for 24 hours a day, it seems like, around the clock to have this complete. The thing that sets us apart from a lot of other construction, we have a construction company here. The thing that sets us apart is that we're integrated in the manufacturing process. So every detail that comes from Drew's mouth is directly implicated into the system that we're building. That way, what would typically take 3 or 4 months to create a specification, our design team is working right with the manufacturing team to allow us to speed that process up tremendously. So.
Yeah, it's definitely a important part of the vertically integrated approach is to be able to design the factory around the equipment, in fact, together with the equipment, so that you can build the factory at lower cost and more quickly.
Yeah, I'm Scott. I focus on cell design. I think it's hard to put into words how inspiring this is. I've been at this for a long time with Tesla, and
yeah,
I really hope others do join us.
Since when, Scott?
Since 2005. Yeah,
yes.
With many of you, but thank you. It. 6. Yeah, year before Drew, but who's keeping track? But I'm really stoked at what the team's been able to accomplish over the last, short period of time, about a year. It's been really an incredible transformation. I mean, hopefully what we've shown you inspires you to join us or join somebody else in the effort. And I couldn't think of a greater, more intelligent, more hardworking team to be working on with this problem.
Hi, Peter. I lead the manufacturing improvement team. And I guess the point that I would like to make is manufacturing improvements is like the accelerator. So like you think about the execution that Rodney talked about in terms of how fast we've been able to put together this factory, which is amazing and something that's been really incredible to be a part of. That's not enough. What we need to do is improve the manufacturing technology. That's the real accelerator. And that's what we're really focused on. Elon talks about it all the time, that really going and improving that system is what will enable us to get to the scale and the cost that we need. And then the other point that I would make is on the recruiting side, like, it doesn't matter if you know about batteries. If you come from any industry, you can do something fantastic in the work that we're doing. We talk to people from industries that you wouldn't imagine. Like, I talked to a guy who makes golf balls, and he has stuff which is really impactful for what we're doing. So, you know, if you're in any industry and you want to be, you know, impactful here, like, come join us. It'd be great.
Hi, excuse me. Hi, I'm Tony. I've been working in lithium and cathode materials for almost 23 years now, and this is the most growth I've seen in a company. I've been here a little over a year and a half. We're hiring amazing people that are allowing us to leverage technology that most of the industry is struggling to achieve. So to answer the question, how are we going to do this? We are really advancing the materials manufacturing for cathodes and for lithium beyond what has been accomplished in the previous 20 years.
It's exciting.
Yeah, my name's Turner. Work closely with the team. I've worked a lot with everyone here, and on the cathode and upstream materials side, it's really important that everyone understand that this growth is coming. This growth is real. We are going to make all of these batteries, and everyone needs to grow with us. The entire supply chain needs to grow with us. And if you have an idea that simplifies anything in the supply chain, come talk to us, come work with us, and let's do it.
Any existing specification is wrong. Any existing
That's
manufacturing method is wrong. Process equipment, it's wrong. It's just a question of how wrong.
Yes.
Quote
Exactly.
Elon Musk.
Yes, exactly. We're wrong. Just a question of how wrong. Just try to be less wrong.
So tell us how we're wrong and how we could do it better so that we can accelerate and improve as fast as possible.
All right. Well, I guess thank you everyone for coming. I hope you liked the presentation. Very exciting future ahead. You know, we're going to work our damnedest to transition the world to sustainable energy as quickly as possible, and your support and help is key to that success. So thanks again. Super appreciated, and look forward to the next event. Thank you.
Thank you.